Okay, let's get ourselves underway. So welcome to day 2. Today we're going to finish this overview of the whole heliophysics system. And the question we're going to get down to not the ground, but basically close to the Earth. And I'm going to ask not only the Earth but other planets why it is the Earth has an ionosphere and a magnetosphere, and other planets, do they have ionospheres and or magnetospheres? And the logic here, you can see that today we're asking why do the planets and the Earth have an ionosphere? And the answer, in short, is because of the sun's corona. Okay? The EUV and X-ray radiation from the corona is what creates the ionosphere. Then you ask, well, why does the sun have a corona? That was yesterday afternoon. I hope you all still remember. The answer was because it has a magnetic field. The magnetic field creates the heat, and then the attempt to get rid of the energy from that heating through radiation leads to a very hot corona and a transition region, which is where all of the EUV and X-ray radiation comes from. So the sun has a corona, we have an ionosphere. Why does the sun have a corona? Because it has a magnetic field. Why does the sun have a magnetic field? Because it has a dynamo. Okay, so these are all sort of linked. But we are now out of the realm of pure plasma physics and into the realm of dealing with a neutral atmosphere. This is the Earth's atmosphere. It's 77% nitrogen, N2, 21% oxygen, a little teeny bit of water, even less in Boulder, Colorado, and some carbon dioxide. And here is the temperature as a function of height. It's traditional, since things up is vertical, to plot the height axis this way, and then this is the y-axis, if you will. And you can see that for a good portion of the atmosphere, the temperature isn't that different from about 200 Kelvin. The sun visible light hits the ground, warms up the ground, and that heat is transported through the troposphere upward, down the temperature gradient from hot to cold. Then we get this weird region of the stratosphere where the temperature actually goes the other way, and then the mesosphere where it's basically in the direction to move heat upward again. So there's this stratopause where there's evidently, since there's a peak in temperature, some sort of heat source. So the atmosphere is being heated right there about 50 kilometers at the stratopause. And then again, we have this portion above 100 kilometers that is the thermosphere. There's obviously a heat source up there. So we have two regions where the neutral atmosphere is being heated. Why is that? Here is certainly one of the most useful plots we have from, for this exercise, and it comes from volume 3. And it is a plot. Now we have wavelength down here and height in the atmosphere here. And in the color code, I've colored it up, but basically yellow is a high amount of energy deposition from the sunlight. And it falls off to purple, and white is virtually 0. And you can see below a certain level, there's no energy deposition because sunlight of that wavelength doesn't reach below that height. Okay? And you can see there's this band of very strong heating around 200 to 300 nanometers. Quite strong around 250 nanometers. I have to keep converting from angstroms, 2,500 angstroms. That energy deposition at 2,500 angstroms is, by and large, what creates the stratopause. That's the source of energy. Now, if we look at, this is the other plot that's going to be very important. This I showed you yesterday, although it was on a logarithmic wavelength axis. I've stretched it out so I could make it match up against this. The blue is the intensity of radiation, milliwatts per square meter per nanometer, from a given wavelength of sunlight. It goes like this. The red is the black body curve. And you remember for visible wavelengths, which are way over here and below, the solar radiation fits a black body curve very, very nicely. We suppress all these nice little Fraunhofer absorption lines. Right around 300, it starts to depart. At first, it's below the black body curve. And then we have this region here, which we talked extensively about yesterday. This is the extreme ultraviolet and X-ray radiation down here from the transition region in the corona. This is basically the stuff we're going to be talking about. It's much brighter than it would be if the sun was really just a black body at 5770. Okay? All that excess emission is coming from the corona, and it's all absorbed up there. I should point out my own personal bias is I like to observe the corona, and the sunlight is not making it below 100 kilometers below the down beyond 100 kilometers from the surface. So if you want to make an image of the solar corona in these wavelengths, such as at 171 angstroms, the most beautiful wavelength to observe the corona in, you've got to get up. And we are currently waiting the launch, which has been postponed, of the High-C rocket, which is going up from White Sands, New Mexico. It was supposed to go up last week. Little fault with the payload, and they've delayed the launch. When it goes up, it'll get up to almost 300 kilometers, maybe 300 kilometers, and make the highest resolution images in 171 angstroms that we've ever seen. And the reason they have to go up on a rocket is they need to be up above where this light can be observed. Okay, but let's get back to what the ionosphere is. And we've sort of seen how this all works. What we need to do to understand this is figure out what happens to these photons, especially these very short wavelength photons, as they enter the atmosphere. And to do this, we just need to work out a probability that a photon will survive. And the probability depends on this thing called the optical path. If the photon has a cross-section for being absorbed by any absorber in the atmosphere, an average absorber, it has a cross-section sigma, centimeters squared. Then there's something called the optical path, which is the density of absorbers, centimeters to the minus 3, times sigma integrated over path length. That is what's known as the optical path. What it means, it's represented as tau. It's the average number of absorbers that's in a cylinder of that total length, right? How many absorbers there are. There's a very key point when you get to 1, so you have on average one thing that can absorb you along your path, you figure you're doomed, right? You're going to be absorbed. Is that right? If I have on average one absorber, one thing that's going to stop me, I will be stopped. True or false? On average, I have one thing that's going to stop me, on average, then I will be stopped, 100% probability of being stopped. True or false? You could ask this in a more quotidian way. You have one customer enters the store every 5 minutes. So you wait 5 minutes, exactly one customer will enter the store. True or false? False. What is the probability 0 customers enter the store in that 5-minute interval? 50%. That's a guess, right? Yeah. Does anyone know the kind of statistics we're talking about here? Sometimes they're called counting statistics. Poisson statistics. So the Poisson probability, if you have an average rate of an average expectation value of mu, then the probability of seeing 0 is e to the minus mu. So sorry, Charlie, you didn't pay your tuition. You can't ask questions. Oh. I don't want to say too much more. I'll get into it a bit later. Okay? It's just a cross-section, right? Absorption cross-section. E to the minus mu. So for 1, it's e to the minus 1. So we often talk in physics about an e-folding issue. Right? That is when you have one absorber, your probability of not being absorbed is e to the minus 1. If there's on average 2, it's e to the minus 2, etc. So you have e to the minus this path length. probability of surviving. Okay? Now, let's then think we have this cross-section for being absorbed, and this is the path length. This is the all-important thing. Think about a photon coming from the sun down to a certain height, and what is my optical path length? Well, first of all, I'm not going to assume the sun is at the zenith, right? It's at some angle chi from the zenith coming down along this path. So first of all, the path length increases while the height decreases, so I get a minus sign. And then I just do a little bit of trigonometry, and I find that the path length is the height interval minus the height interval times the secant of this angle. Okay, so if I'm at zenith, secant of 0 is 1. Secant is 1 over cosine, so it's 1. So my height is basically the same as my path length, but just backwards. As the sun gets lower, the path length actually gets to be a larger multiple of the height. And as it goes to sunset, well, we're talking about a planar atmosphere. This isn't a spherical Earth. So actually, it goes to infinity. Secant of pi over 2 is infinity. So it would never actually reach me. Anyway, that's the simple calculus. The other thing I'm going to assume, and this is very crude, but it helps us get some math done, and that is that the density, the number of scatterers, is falling off exponentially with height. It has some density at the ground, and then it falls off exponentially with another very important number called the scale height. This is the pressure scale height or the density scale height. And so the number density scales exponentially with height. When I do this integral, I get a path length that is this absorption cross-section, the number density at the ground, h, and then my secant, and then my exponential. I can clean this up a lot if I basically define this to be something else. In other words, I take the logarithm of this and call that a height z tau 1. I believe it's called something else in the literature, but I like the fact that this reminds me, this is the height at which tau is equal to 1. And it's basically the scale height and then the logarithm of all this stuff in here. And when I do that, I basically have this function here. The path length is an exponential decreasing with height. So as I go to, if I go to very, very high heights, the path length is, the optical path is 0. Essentially, I have 0 scatterers if I get to infinity. If I'm on the ground, I have some other path length. Okay? Now here is the cool part, in my opinion. That makes the probability of surviving to a given depth, z, a given altitude, an exponential of an exponential. I've never in my years seen a function except in this one application. We get an exponential of an exponential. Okay? That is the probability of surviving down to that height. And we are out of batteries here, so we're on manual. So if I plot this, I basically can plot what is this e to the z tau over h. That's basically the cross-section. And what I find out is that's really the actual scattering cross-section that I have, that I observe, divided by some factor that involves only the mean mass of my scatterers, the gravity of Earth, the pressure at the ground, things we know. Okay? And I can just plug in all the numbers, and I get 5 times 10 to the minus 26 centimeters squared. It reminds you that atoms are very small. Okay? This is basically the area under one atom in the atmosphere. If I go all the way up with this cross-section, I will have one atom in my atmosphere. And if my scattering cross-section is bigger than that, my absorption cross-section is bigger than that, then my tau equals 1 surface must be higher up than the ground. If it's smaller, then tau equals 1 would be below my feet. That doesn't really mean anything, okay? But that's just basically it. And here is that plot of that exponential of an exponential in blue, and the red is showing me where the tau equals 1 surface is when my cross-section is 10 to the minus 17. This is actually a pretty typical number. This is typical of a different wavelength, typical of yet another wavelength. You can see for this, you would think, wow, this is, what is that, 7 orders of magnitude larger than this canonical cross-section. But because it appears in a logarithm, that just basically puts the scattering cross-section up there. As I increase, the scattering cross-section comes, or as I decrease scattering cross-section, then the height of tau equals 1 moves downward. So far, so good? All right. Now, Charlie asked me to talk about this cross-section. And I don't want to go through all the details of how atoms absorb light. I will just say, here is a plot in units of centimeters squared of what this is as a function of wavelength. This is vastly simplified, but it's basically saying you have air, you have photons of this wavelength, say 50 nanometers, 500 angstroms. It has a very large cross-section for being absorbed. And as the wavelength decreases, there's some nutty stuff going on here. That's a lot of interesting details, but we can't really talk about them. And then the scattering cross-section falls off as the wavelength falls off, increases, sorry. So that scattering cross-section is basically the logarithm of that gives me that height, the height at which I'm going to E-fold, where my probability of surviving is 1 over E. Okay? And I basically can take that same plot and plot it as the Z tau 1. And here it is. And here you have, this is from a lecture, but I think there's something like it in the book. This shows you the kinds of physics that's going on to absorb these photons. For this 2,500 angstrom absorption, what we really are looking at is mostly ozone is absorbing photons, 2,500 angstrom photons. This is why ozone is considered important for, for dropping down the ultraviolet light. It's actually keeping the light from penetrating below 50 kilometers. Okay, so as long as you're below 50 kilometers, you will encounter a lot less 2,500 angstrom photons. We also have absorption by oxygen molecules, nitrogen, oxygen, and all-important photoionization. That is, the photon that's being absorbed is being absorbed because it's knocking an electron out of the molecule. Now, the only molecule I understand, the only atom I understand, is hydrogen. Okay? Does anyone remember how much energy in electron volts it takes you to knock the electron out of the ground state for a hydrogen atom? 13 electron volts, yes. Does anyone remember the wavelength associated with that, a photon with 13 electron volts? The classic, certainly for astronomers, it's a well-known wavelength. (912 angstroms, 91, right? That's called the Lyman continuum. Okay? 1216 is even more famous. That just knocks it from the ground state up to n equals 1, n equals 2. Sorry. So 900 nanometers, that's where hydrogen would be. It's not on here because there isn't much hydrogen in the atmosphere. But suffice it to say, from a standpoint of an astronomer, atoms and molecules are atoms and molecules, right? So you get sort of tens of eV. I believe for oxygen it's like 12 eV to ionize it. For nitrogen it might be more like 15 eV electron volts. So it's all in that ballpark, and it's around this wavelength that you're being absorbed because you're knocking electrons out of the molecules. And this is all important for the ionosphere. In fact, it's these shorter wavelength photons that are really doing it, because they're knocking out the electron and then giving the electron some energy so it can get away. Right? You don't just want to pull it out. You want to pull it out and throw it away. So there you have it. This is the height of tau equals 1, where the photons are going to be absorbed. And if we know the probability of a photon making it, then we can sort of see, okay, this is why this plot looks this way. Essentially, this curve here is mirroring the cross-section for absorption. Right? So the reason that the EUV photons are absorbed so high up in the atmosphere is they have such a high cross-section for being absorbed. And then we have this bump here that comes from all of this oxygen absorption. And then this bump here, which is actually giving rise to our stratopause, is absorption from that bump in ozone. Now, the energy flux is basically the number of photons I started with times the probability that they've made it to a certain height. So this is the flux from the sun reaching 1 AU, and this is the flux down to the height z here, because it's weighted with the probability. If I take the derivative of that flux, I have how much energy didn't make it. This is the energy deposition, right? And now I have to take a derivative of this really cool function. The exponential of the exponential, it brings out another exponential, and I have this very interesting function that is an exponential of an exponential and a linear function. Even better. This kind of function is commonly referred to as the Chapman layer. And I've plotted it here in red. Here is the probability, but it's on a logarithmic scale. And you can see on a logarithmic scale even, the exponential of an exponential is very sharp. It falls off very rapidly here. So the energy deposition has this floor on it, and it has this tail. Now this is an exponential decrease, so on a linear scale you'd hardly be able to see any difference. But this is, at least logarithmically, this is more gradual fall off than the bottom. This is where the energy is being deposited, and you can sort of see that structure here. This is also a logarithmic scale. This is log, I cut off here, yeah, log 10 of the absorption, and so we have that hard floor and basically this exponential fall off, which is linear in the logarithmic scale. Oh, that's confusing. So here is my I infinity, 300 milliwatts per square meter right here, and basically that turns into this level of energy deposition. It all just works out this way. That then tells me why we have so much energy being deposited here. It's because there's so much more light in this region here. So even if the sun didn't have a magnetosphere, look, if the sun didn't have a magnetic field, didn't have a corona, this is black body, so we would still have this ozone layer. But this region here is really coming from the corona. Right? So this energy deposition is coming from the corona. And it's that that's doing the photoionization. So from this wavelength range here, basically 100 kilometers and up, and 100 nanometers and shortward, we are getting ionization. And here's sort of a chemistry picture which shows you the different kinds of ionization we get. We can ionize an N2 molecule, and that will create some N molecules. We can ionize a pure oxygen atom, and we'll get a positive oxygen ion, oxygen molecule, etc. All of these ionizations are going on in this little region here. And basically, it means that in this region of the atmosphere where that ionization is happening, we are creating electrons and positive ions in pairs as we photoionize them. And lo and behold, that is where, if I plot the electron density, and this is in electrons per cubic meter, and of course, here they're assuming you realize that every time you create an electron, you're creating a positive ion. So there's exactly as many positive ions as there are electrons. They're just going to plot the electrons. And we see nothing below sort of 70 kilometers because none of the photons at that short wavelength that can photoionize make it below that altitude. So you just don't see any free electrons there. And then all the free electrons are in this layer here. This is the ionosphere. Okay? And all these photons are coming from the transition region in the corona. Very important. So we talked yesterday about why there even is a corona, and therefore there's a transition region. That's what gives rise to all these wavelengths. That's what gives rise to the photoionization and the ionosphere. So far, so good? Yeah? Yeah. Yes, I glossed over a whole topic called radiative transfer. So you can actually basically are you talking about the fact you can photoionize something and then you can have another recombination that emits another photon, or you can scatter that photon and you'll make it down. Yeah, this is a very hairy subject. I tried to make the simplest argument possible, saying that once a photon is absorbed, it disappears. But you can recombine and then re-emit that photon, which is essentially the same as if the photon came in and was scattered. And if it's scattered, it's not going along the same path, but it could make it further down. Actually, it's going to go off in all directions. Yes, it becomes very complicated. Does that answer your question? Yeah. Yeah.
I think I've read that around 90 physics or in the D region, you have to get large populations of negative ions to outnumber the electrons.
Okay. Tim, can you answer that? Negative ions. Why the heck do we have negative ions? Wow, okay. Thank you. If he can't answer it, then what chance do I have? Sorry, but it's an interesting question. This doesn't fit into my very simplistic view of what's going on. All right, so here is the way we explain the density of what these things are. That is, we have electrons and ions being created by photoionization. And the rate of production is proportional to this flux, that we already worked out. The density of scatterers, which I'm assuming here is an exponential, just to make my math easier. And a cross-section that really has to do with the total cross-section for ionization over all wavelengths, and just the ionization part, not absorption by any other mechanism. So it's slightly different than the other sigma I was using, but suffice it to say we get the same Chapman layer profile. There's no z tau 1 here, but I could basically add it and subtract it off in the prefactor. We get the same production rate for electrons as we saw for energy absorption. It has that same structure, and here it's called Q. This is the number of electrons produced per time per volume. Okay? And you'll notice it depends on the number of things that I can ionize. Here, I am tacitly assuming, I'm tacitly assuming this is the same as if there was no ionization going on at all. So in other words, I'm ignoring the fact that I've already ionized some fraction of them, and those aren't available to ionize again, not at that wavelength anyway. We'll see that that's a fine assumption to make. But then that basically would say that I just keep ionizing things continuously, and I would eventually run out of neutral atoms, except for something they call electron destruction, but it's really those electrons can recombine with the positive ions and form neutral atoms again. So basically we have production and we have destruction. Okay, now this is actually rather complicated. If you go into the physics of combining a positive ion with an electron, it turns out it's very difficult to do and conserve both energy and momentum. So there's a lot of chemistry or complicated physics that goes on here. I'm going to ignore it and just say, well, whatever happens, you can describe with a coefficient alpha, but it does depend on the product of the density of electrons and the density of ions. And this actually appeared yesterday when I was trying to argue how much radiation occurred. I didn't draw attention to it. It basically has to do with how many collisions there are. You can only produce this neutral atom if an ion collides with a positive, with an electron. And so the rate is going to be proportional to the square of their densities. Sorry, the product of their densities. So that's why in a lot of these scattering problems, we do get these densities products. Or if I assume that there's the same number of positive ions as electrons, because actually they had to be created in pairs, then the loss rate is proportional to the density squared. This is basically the same reason that we have brightness in X-rays that's proportional to the density squared. It's proportional to the rate at which things are colliding, and that's this. Now, if we have an equilibrium, then the energy, the rate of production is balanced by the rate of destruction. The two balance each other out. So I can set this equal to that, and I can solve for the density of electrons. It's going to have to do with this density of production divided by this coefficient that contains a lot of physics I didn't want to discuss. Both are functions of height. This has that really cool profile, so you expect the electron density to have the square root of this cool profile, which on a logarithmic axis means half of this square profile. I didn't give you any axes here, so you don't even know what half would be. And lo and behold, that is what happens in equilibrium. As long as we're producing electrons, they are being destroyed at the same rate, and basically they reach equilibrium. Now, we don't always have equilibrium. First of all, half of the time, the sun is not shining, and we are not producing any more electrons. But that doesn't mean they all go away, because actually what happens is then you just have to go through loss with no production, and they will decay away. This goes as the density squared, so their rate of decay depends on how many there are. So as they decay, they will start decaying more slowly and more slowly. Suffice it to say, this is what happens. We basically have an equilibrium during the time when the sun is up. Right? We have this peak in the electron density, and here I'm plotting electron density, and this is in a linear color scale, and this is over the Millstone Hill radar in Massachusetts. This is a model. But basically, here's where the sun is on, and it's photoionizing, and then the electrons and ions are recombining, and you get an equilibrium. And then the sun goes down, and we stop the source. And what you see is low down, the minute you shut this source off, the electron density goes right down. It starts to recombine. Actually, very low down, as the sun gets lower in the sky, it's not even reaching these heights because of that secant. So it shuts off even earlier. And then up here, it takes quite a while for the electrons to recombine back down. On a logarithmic axis, it doesn't go away at all, but it does drop by here. It looks like 3 orders of magnitude. That's a big shutdown. On a linear scale, it looks like 0 here. Okay? So basically, as you might expect after this story, the ionosphere gets a lot less dense in the nighttime when there's no photoionization going on, and you're basically there because it's still taking you a time for the electrons to meet up with the appropriate ion and recombine. Okay, so there is this day-night variation. And the other thing to see is as you go up higher, the densities of everything are intrinsically smaller, and so it's taking longer and longer to decay away. So here is a picture in equilibrium of what's going on. And this is a very complicated graph, but what we have is the black curve is the electron density in centimeters to the minus 3. Here is that region. It doesn't even start. This is 100 kilometers. It doesn't show anything below that because there's virtually nothing to show. The dashed lines here are the neutral species. So you'll see nitrogen falling off. You'll see oxygen falling off. You can barely see in this light, there's a cyan line that is atomic oxygen falling off. And then there's helium in the atmosphere. Even though it was discovered in the sun, it does exist in the atmosphere. And it's falling off very, very gradually. Here are the ionized versions of those. So here's the ionized oxygen, right? Oxygen atoms. Matching the electron density, which is telling you that mostly what's being ionized here are atomic oxygen. It has a lower ionization threshold, so there's easier to do the ionization there. That's what's producing most of the electron-ion pairs. There's also some molecular oxygen being ionized, etc. A key point. Look at this. This is 10 to the 6. Good number density for electrons. The number of atomic oxygen atoms to compare it to, and actually those are the dominant ones here, 1,000 times higher. So something to always keep in mind, when you're talking about the ionosphere, you're talking about the electron-ion pairs. They're only 0.1% of the things out there. The ionosphere is 99% neutral at its sort of peak area, and this is just a rough number, right? We just saw that it all varies. So this electron density falls off at night, but it's almost all neutrals. Nick? Yeah, I'm sorry. You can blame Stan Solomon, I believe, for this. I should have. Yeah, okay. So it's sort of a background question. Why do these things fall off at different rates? I will say this. They are all roughly at the same temperature. But the number of nitrogen molecules per cubic centimeter is getting smaller, faster than the number of atomic oxygen molecules. Why does that happen? Mass? What does mass have to do with it then? The scale height, yes. Do you know that formula for the scale height? MJ, it's KT over MG. What you quoted was the much more useful inverse scale height, which is what you have to multiply. Yeah. So as the temperature goes up, the scale height goes up. These basically all fit. And so, sorry, I should have put it in here. Even more importantly, it's e to the minus z over h. So the scale height is telling us how fast this thing is falling off in an exponential. And so when I have a mass of 28 protons, like a nitrogen molecule, it falls off with a scale height of 43 kilometers. Oxygen, 38 kilometers. They sound similar, but you put them in the exponent, and the oxygen molecules are falling off way faster. And I, of course, made the same crazy color scheme choice here. Atomic oxygen, 76 kilometers for a scale height. So it's falling off much more slowly. I mean, that's a factor of 2 different, obviously, than the molecular oxygen. But in the exponent, that means by the time you get up here, atomic oxygen is dominating. And except until you get the helium dominating, which falls off with an amazing scale height of 300 kilometers. All right, so just to summarize where we've gotten to so far, the ions and electrons, they form a plasma. So a lot of the things we know about plasmas will apply to them. There are overwhelmingly more neutral atoms, okay? And these you can think of as an entirely separate fluid. However, these two fluids are very strongly coupled. Probably for no reason more important than the fact that they're constantly changing roles, right? Neutral atoms are becoming ions, ions are becoming neutral atoms, and so whenever you have that kind of exchange, it basically introduces an extremely strong coupling. So it creates a drag force. So ionospheric physicists talk about these fluids as separate fluids, but with a very strong drag force coupling them. The reason the ions and electrons as a separate fluid are so important is they are basically the things that respond to electric fields. One of the things they will do is they'll act as a conductor, and they will screen out any electric field that oscillates more slowly than the plasma frequency. And I've worked out, here's the plasma frequency, not the angular frequency, which we're used to seeing. This is the linear frequency. It's basically 10 kilohertz times the square root of the number density in inverse cubic centimeters. This has profound consequences for radio astronomy. As a solar physicist, I would love to see the solar corona at a lot of different frequencies. So my question, what is the lowest frequency I can hope to observe the solar corona at? What? 10 megahertz, right? The radio astronomer. First of all, I'm at a disadvantage this way because I'm looking at the sun, which is creating the ionosphere. If I were a nighttime astronomer, God forbid, I could do this at night, and the ionosphere would have a lower density. But if the density is 10 to the 6, I take the square root, I get 10 to the 3 here, 10 megahertz. You'll see plots sometimes that have radio data, and they go across that band. everything at frequencies lower than about 10 megahertz has to come from a spacecraft. So you pay dearly for every bit of data in that lower frequency wavelength. The stuff above that just comes from a radio dish on the ground. Not cheap, but doesn't cost what it costs to put stuff into space. All right. So now we're at the point where we start to see how the ionosphere responds to the corona. I showed this plot yesterday. This is the X-ray flux. This is 1 to 8 angstroms. Much shorter wavelengths than are creating the ionosphere, but it varies by a factor of 50 from solar min to solar max. We saw that yesterday. That comes about because the corona itself gets much more dense during the solar maximum, and we talked about that. So that means there are ionospheres that are created by a lot of EUV and X-ray flux from the corona at solar maximum, and then there's a profile that describes what it looks like at solar minimum. So the ionosphere actually has profiles that differ obviously between night and day, but also between solar max and solar min. Okay. Very important thing there. Remember, this is the density. Let me also pose the following simple thought question. I showed you one plot where I showed that this number here goes up by another factor of 100 during a solar flare. X-ray flux in this wavelength can go up to a factor of 100 even more, brighter temporarily. The photoionization band is not going up by that much, but it will go up by, let's just, for good numbers, put in a factor of 10. Let's say the ionizing radiation is increased by a factor of 10 just for a few minutes. But what will that do to the production? What will that do to the density, equilibrium density of electrons in the ionosphere when we see a flare like that? Energy flux, or photon flux goes up by a factor of 10. Electron density goes up by equilibrium. Actually, very complicated physics that goes into all this, but by 100? Yeah, 100? Everyone happy with 100? 3? 100 is 10 squared. 3 is square root of 10, as anyone would know. Yeah, it's actually the square root of that production, the flux. It's the square root of the flux. So it goes up by a factor of 3. That's pretty good, right? So this is something we're going to come back to. And I think Tim will probably talk about, well, maybe not. But some people will talk about the way the ionosphere responds to just the solar flare itself, just the X-ray flux. And this is basically another plot due to Jan Soika that shows different levels of solar radiation and what the ionosphere looks like and this is a characterization basically of the amount of X-ray flux. Okay, so it basically moves the ionosphere up a bit, but definitely increases the number density up by that much. All right, so that's the ionosphere on Earth. How about some other planets? Well, we have Earth with our nitrogen atmosphere. We have Venus and Mars actually have very similar atmospheres, if you just look at this, mostly CO2. So that's going to be a big difference there. The atmospheres themselves, the temperature at the base of Venus is very high, as we all know, but it falls off. They both lack this turnover here, which, as I saw, was caused by ozone, and they don't have any oxygen. So my assumption, not that I do this for a living, is that without the oxygen, they just don't have this feature in their atmosphere. It just falls straight off, and then we form the thermospheres up here. This is what the ionosphere looks like, and here we've plotted each of the species, but basically the electron density would just follow this outer profile. And in Venus, we get a density that's not too different from the Earth's, sort of up around just shy of 10 to the 6, and a roughly similar altitude as well. And this is all caused by the This is mostly caused by the photo dissociation that results from CO2 being ionized and creating oxygen, etc. So up there, we get that ionosphere. Mars, very similar diagram here because it's a very similar chemical composition. It's a little further from the sun. The densities are lower, so its ionospheric density is lower. But both of those planets have neutral atmospheres that create ionospheres. I'm not going to go into the ionospheres of the giant planets because I want to move on to discussing what happens when the solar wind, which we talked about yesterday at length, comes in contact with Mars or Venus. Simple cases because they don't have magnetic fields, but they do have this ionosphere. It's an electrically conducting layer. In fact, as long as the solar wind isn't varying on microsecond timescales, it looks like a perfect conductor. So we have a conducting sphere in the middle of the solar wind. Now, the solar wind material doesn't really care about the conductivity. Actually, the particles collide so infrequently, it's unclear it would care that much about Mars or Venus. The magnetic field, on the other hand, is holding on to those particles. It cares. It knows about Faraday's law. It knows that it can't penetrate into a conductor in a short period of time. So as far as the magnetic field goes, and therefore as far as the whole solar wind goes, it sees a spherical obstacle. It sees this ball that's impenetrable, and it has to go around it. The other thing we saw is by the time you get out to 610 solar radii, the solar wind is going supersonic. So it is an obstacle in a supersonic flow. Okay? Supersonic flows are really cool. As they encounter something, the wind has no way of knowing that. Okay? It has no information coming from downstream. So it just gets totally surprised by this spherical object. Well, what happens is we form a shock. Shock is, I heard it once beautifully described, shock in hydrodynamics is a hydrodynamic surprise. It is something where the fluid upstream has no way of knowing what's going to happen, and the shock is saying, hey, wait, there's something downstream we've got to go around, because it's a perfect obstacle. And so in this flow here, it's actually subsonic. And it's subsonic for two reasons, but one main reason. The first reason, which is sort of not that important, is the flow slows down a bit at the shock. Okay? But actually, if it's going 8 times the sound speed, it can't slow down by more than a factor of 4. So doesn't that make it going twice the sound speed after it slows down? So it's still supersonic and wouldn't know what's ahead of it? Why is that not right? What? Temperature goes up. Temperature goes up a lot, which means the sound speed goes up. So its velocity's gone down, but the sound speed's gone way up. It's very subsonic over here. That's a recipe for saying, hey, let's go around this thing. So we get this subsonic flow, which is the sheath flow, behind a bow shock. Very simple problem. In fact, you can work out the solution with a bunch of assumptions analytically and figure out how wide this layer is. Okay? What you assume is the inflow is just a really big Mach number. I don't even have to give you a number. It's just much, much greater than 1. It has some density that is, well, prescribed by the solar wind. When it hits the shock, it is a high Mach number shock, so the density increases by a factor of 4, the flow velocity decreases by a factor of 4, or the normal component of the flow velocity decreases by a factor of 4. The Mach number becomes very, very low. When you're at very, very low Mach numbers, no matter what material you have, your flow is incompressible. Okay? That's sort of why we have incompressible flow. It's not because you have fluids that are incompressible. That's one of my pet peeves. People who think there are incompressible fluids and therefore incompressible flow only applies to them. Incompressible flow applies to the air. Right? I was saying yesterday, all airplanes before World War II were designed using incompressible fluid dynamics because they never flew faster than the speed of sound. Everything was subsonic. Everything's incompressible. So if we have an incompressible flow, I can express it in terms of a stream function I turned out to have stolen this stream function, which gives me the behavior I need from Lightman, a very smart individual. And if I use this, I can figure out what the radial velocity is and what the tangential velocity is. The radial velocity going inward at the shock, tangential velocity. I have to match the conditions that basically the radial velocity decreases by a factor of 4. Oh, this shouldn't be minus. Yes, it should. By a factor of 4, so it's a quarter the upstream radial velocity, and the radial and the tangential velocity has to be the same. Yeah. Oh, sorry. Rankine-Hugoniot conditions. The Rankine-Hugoniot conditions are a very complicated set of equations that come from some complicated relationships that conserve mass, momentum, and energy for a gas being shocked. And if our gas is a monatomic plasma, then it turns out that the asymptotic level of density compression, that the most you can compress by, is 4. If you have a neutral gas, sorry, it's not neutral, if it's a diatomic gas, turns out it's 6. So I'm afraid we don't have time. Merev Ofer will talk about shocks. But just take it from me that your maximum compression ratio you can get from a shock is 4. And that is what we're assuming here. And so if the density goes up by a factor of 4, and you conserve mass, then your flow speed goes down by a factor of 4. When you're driving in traffic, it usually works the other way. If all the cars slow down, then the density of cars goes up, assuming no cars are being lost anywhere. You just basically have to conserve cars. You have to conserve mass. So your velocity goes down by a factor of 4. Your the density goes up by a factor of 4, but only in the normal direction. OK, you match those. You basically get the following. This distance here, which appears inside this thing to the 5th power, has to be the 2/5 ratio of 3/2. Has to basically be, sorry, yes, this is right. 18% bigger than this. So the thickness of the sheath in this simple calculation is just set by a fixed number. As long as the Mach number is really, really big here and the Mach number is really, really small here, we get a simple layer like this. When we did numerical simulations, and this was done by Spreiter in the 60s, it's these black curves. So these black curves here, you see over here in this region here, where we really trust them, this isn't such a bad approximation. And in fact, our estimate of how thick this is very close to the one you really get. A more important, or another consideration here, is what happens to the temperature. Now, as John pointed out, when the flow slows down, its temperature goes up. What has happened is you've taken the mean kinetic energy, the kinetic energy of the center of mass, 1/2 m u infinity squared, and converted a fraction of that. The fraction is 3/8. Again, this comes from Rankine-Hugoniot conditions, to heat. That's why your temperature goes up. Your kinetic energy of motion is converted partly to heat. The rest of it continues on in kinetic energy of motion because you haven't stopped. You've only decreased by a factor of 4, as well as the fact that you had to do work to compress, et cetera. You get 3/8. That is the stuff going here. If I look at a 400 kilometer per second wind, that temperature should be 3 megakelvin. That doesn't depend on the initial temperature. Right? This just depends on the velocity. This is assuming that the initial temperature was maybe 0. It's not 0, but it's a lot lower than 3 megakelvin. So you shock and you heat up to 3 megakelvin. Then you slow down, convert some of the remaining kinetic energy to heat, and you get up to 16/15ths of that. This is a lot of fun use of Bernoulli's principle. And the pressure ends up going up like that. So you have very high pressure here that is basically the ram pressure of the upstream flow. But the flow here is stationary. The flow here is stopped right at the nose. So it is in this sheath that we convert a lot of the upstream flow energy to heat, to temperatures. We saw in the overall plot of the heliosphere that we had a source of heat right here. That's part of it. It's this shock that is converting the bulk kinetic energy of the solar wind into heat at the shock. Okay. Here's a little picture of someone's cartoon of what this looks like around Mars. There's the bow shock. There's a bunch of stuff from the ionosphere, all kinds of cool stuff going on in the ionosphere. This is basically the sheath region we were talking about here. Just want to focus on that, or just mention that part. This part I haven't even come close to explaining. Very similar picture for Venus. We have the bow shock. We have the sheath. And of course, downstream, none of that analysis we did applies, but there's that region that we worked out the detailed structure for. Let's see. I think we should take our 5-minute break before we move into magnetospheres. So let's just give ourselves a little pause and try to get ready to think about the magnetosphere. Start up again in 5 minutes. Yeah. Oh, okay. Good. We're here. Hey, good to see you. It's embarrassing to have to present this with you here, but yeah, it's very crude. So this is maybe a question. The ionosphere becoming collisionless. So I think the ion-neutral collision rate is always going to be pretty high because you always have to basically be producing one from the other.
Yeah, I mean the ions at about the ions at about 300 kilometers. They incline about once every 60. So there is still ion-neutral coupling even up to 3. Eventually, but even the ions won't be collisionless even when you get out into the magnetosphere, because the Coulomb interaction.
Yes.
So it still behaves like a collisional Coulomb attraction between plasma is so it's still collisional, although it's not the individual one. But when it gets down to below about 400 or 500 kilometers,
Yeah.
Was that your question? Yeah, I think that's kind of
There is this sort of exosphere, but that's, in my understanding, people are mostly talking about neutrals being collisionless. And neutrals can be very collisionless because they don't, there's hardly any ionized material for them to care about. The ions and electrons are like, we came from the neutrals, so how can we ignore the neutrals? We're constantly exchanging. Hydrostatic equilibrium does not involve collisions. Pressure does not involve collisions. This is a big misunderstanding. Yeah.
No, the reason I'm asking is I work on Python's ionosphere a bit.
right.
Oh.
Scale heights of ions in the ionosphere, and they don't look like they're hydrostatic equilibrium at all. So when I saw your plot,
Hydrostatic equilibrium, then, to depart from that, I will say this just from a plasma physics standpoint. The key issue there is probably flows. Supersonic flows. The minute you have supersonic flows, now the pressure forces aren't going to be that important.
Yeah, I mean the fluid approximations for the Earth's atmosphere they're okay up to about 600 kilometers. So yeah, and you can work out what it's when the mean free path scale height is sort of 40 or 50 kilometers. So when the mean free path gets so long, then the collisions are so infrequent, and they're just free particles. So for the Earth, that boundary is about 500-600 kilometers. I mean, it depends on the temperature. It stands in facts. So you can apply the hydrostatic balance up to that altitude.
I would argue you could Yeah, I'm still live, but that's okay. You could probably, I mean, if you have a completely collisionless collection of Maxwellian distribution of particles, it will have a equilibrium. It will have an exponential scale height. Regardless, no collisions required. Now, how would it become a Maxwellian distribution? That's collisions. So above 600 kilometers, you're going to start to say, oh, maybe this isn't really Maxwellian, and therefore, maybe I really can't even tell you what the scale height would be. Something makes it Maxwellian. Even you can. I don't know what you really do have, but I'm just saying from a basic plasma physics standpoint, if you take non-interacting particles, put them in a Maxwellian distribution at one height, it will be a Maxwellian distribution at all heights, and the density will fall off with the scale height.
Okay.
Now the temperature will be the same everywhere because they have no way of exchanging any temperature.
Okay.
So you get isothermal atmospheres from zero collisions, provided you have an isotropic distribution. that's begging the Titan's atmosphere. You're saying
The observed scale height, larger.
the gravitational scale height. Yeah.
But I mean, there's a lot of capacities in the electron.
Ooh. How ionized is that? Is it like this? Is it just very weakly ionized? Is it mostly neutrals?
Mostly neutrals as well, but it's over quite often the models do that.
Yeah. Yeah. Nor did I.
Not a main problem on the
Yeah, no, that's I didn't know that. Okay, yeah, it's actually fascinating because when you go into the details of when you expect this hydrostatic balance, really doesn't rely on a lot of things, but there are a few things that can go wrong. The ones that I know most often in the solar convection zone are flows. Once you have supersonic flows, now the pressure is not a significant player. It's the inertia of the flow that's the significant player. That can have a big effect on it. Otherwise, through the whole convection zone of the star, it's hydrostatic.
You were saying that
Yes, thanks.
hydrostatic balance, you're saying doesn't.
It does not depend on collisions. Yeah.
And that's based on.
It's just based on kinetic theory. You look at kinetic theory, because pressure itself doesn't depend on collisions in the sense that you get the pressure is just a second moment of the distribution function. Okay, that's a different issue. Whether it behaves like a fluid, that is, you can well, no, I would say yes. However, it's usually a tensor. It's usually a tensor. If you can't isotropize the distribution function, then you have a pressure tensor, which actually you have in.
Atmosphere and the ionosphere, I think that deal with then you can apply that kinetic theory.
Yeah.
In the fact that it's fluid, so you have the concept of temperature, the concept of pressure, gas, all of those things.
Of all the things, no matter whether it's a fluid or not, you just have a collection of particles. Okay, you have a pressure. We should talk about this more over lunch. Okay. So now I just gave you a very quick rundown of what we expect to happen in the case where the solar wind encounters one of our unmagnetized bodies. That because it has a neutral atmosphere, I didn't talk about the moon. It doesn't even have an atmosphere. That's an interesting, but we're not going to talk about the interaction of the solar wind with the moon. But when it hits a body with an ionosphere, it sees a conducting ball, and it forms a bow shock, and a sheath region around that ball. When it hits one of the magnetized planets, Earth, Jupiter, Saturn, etc., actually it's the magnetic field that, as we said, is generated by the dynamo of the Earth. Or, yeah, I'm going to mostly say Earth. If you really prefer to work with Jupiter, substitute the word Jupiter. Just basically our planet has a magnetic field, and the solar wind, which is a conducting plasma, interacts with that magnetic field first. Now, the first thing that you can notice is, well, this region that has a magnetic field from the Earth is going to present an obstacle to the solar wind the same way our sphere did. It's just more of a squishy obstacle, right? It's not a solid ball, but it's basically something where the magnetic field of the Earth is going to create this little region that the solar wind has to avoid. Same problem, though. It's a supersonic wind hitting an obstacle. It creates a bow shock, and it creates a sheath. Exactly the same analysis. That sheath, in the simplified analysis I gave you, is 18% as wide as this magnetopause distance here. That's called the magnetopause. But it's not a solid ball, so where does that pressure come from? We worked out the pressure over here. The pressure over here was basically 4/5 of the ram pressure. That's how much pressure is built up at the nose by taking the inflowing kinetic energy, converting it to heat here a little bit, and then a little bit more here. We got that 4/5. That pressure is on the outside, and I am going to take the very bold assumption of us ignoring the magnetic field pressure of the solar wind entirely. I also ignored this magnetic field pressure when I did that other problem. But the magnetic field pressure from the Earth is pretty much all there is. Okay, so we have this Earth's magnetic field, and I'm going to go back to my potential magnetic field assumption, the assumption that the magnetic field around the Earth is curl-free. Not a perfect assumption, but it has gotten us a lot of mileage, and it'll get us a lot more. And so I have to solve Laplace's equation inside here. We do it with spherical harmonics. Here I'm only keeping the L equals 1, the dipole harmonic, and it has the decaying piece that goes as 1 over r squared. That is actually the part that comes from the dynamo. We talked about that yesterday. So I have a potential and therefore a magnetic field that goes as 1 over r cubed. That's the dipole magnetic field. But the magnetic field has to be confined inside this shell, so that can't be the whole story. We actually have to have the increasing piece as well. When we did this for the magnetic field of the sun, our boundary condition was that the magnetic field of the sun had to be radially outward at this artificial outer boundary. Here at this boundary, the magnetic field has to be tangential, not normal. So instead of a Dirichlet condition, I have a Neumann condition. And here I've solved Laplace's equation with a Neumann condition. I get a second term, which is due to the image, if you will, of the dipole. This is the solution for a magnetic field from a dipole that's confined. Actually, let's be honest, I did this confined inside a spherical shell. The radius of that shell I don't yet know. That is the radius of the magnetopause. But that is the magnetic field. Here's the magnetic field pressure. I basically take the gradient of this, square it. No surprise, I get something that goes as the Earth's radius to the 6th power, the magnetopause radius to the 6th power in the denominator, right? So I take the gradient, I get 1 over r cubed, and I square them, and I get 1 over r to the 6th. So far, so good. This is the magnetic pressure just inside here. The pressure balance, then, is that this magnetic pressure on the inside must balance the pressure that's built up in the magnetosheath due to converting ram pressure to real plasma pressure. When I put in that balance, I find that the magnetopause distance from there out to there should go as the magnetic field strength of the Earth and then divided by the ram pressure of the solar wind to the 1/6 power. Very interesting relationship here in Earth radii. Okay? If I put in some numbers here, that's about 12 Earth radii. Okay? This is for a solar wind speed of 400 kilometers per second. We saw that that's a pretty typical solar wind speed. And a solar wind density of about 10 to the minus 23 grams per cubic centimeter. Very low density. We're very far away from the sun. Okay, so I get about 12 Earth radii. Now I want to take a little quick break here for some intuition. The satellites, we have a bunch of satellites that are geostationary. SDO is one, the GOES satellites are another. More importantly, our satellite TV satellites are in geostationary orbit. How many Earth radii are they orbiting at? I had this number over dinner last night. 6. 6.5, right? If you don't remember it, one thing you could remember is that at low Earth orbit, if you're just going a couple hundred kilometers above the surface of the Earth, you orbit once every hour and a half, roughly. Then you have to remember Kepler's third law. Sorry, geostationary, you're going to orbit 1 in 24 hours. Kepler's third law is that that ratio of radii is the ratio of periods to the 2/3 power. Okay? So 24 over an hour and a half, 24 hours over an hour and a half raised to the 2/3 power. Okay, I will admit it's challenging to raise this number here to the power 2/3, but when you do, you get 6.5. So our standoff distance to the magnetopause is 12 Earth radii. Our satellite TV satellites are safely inside the magnetosphere. Thanks to Nick's lab yesterday, we saw that that doesn't always help. What has caused in that event? Why was it that the magnetopause moved so far in, right? So that this calculation, I will claim this calculation still applies, but one of our conditions, it's this calculation here, has changed that brought the magnetosphere into 6 Earth radii and left the GOES geostationary satellites outside the protection of the magnetosphere. What had changed here? The magnetic pressure, right, which I've ignored, did come into play. The solar wind had a bigger magnetic pressure. Also had a bigger density, and I think a bigger velocity. So 2 things went into the denominator there. The Earth's magnetic field didn't change. That was not what happened. But the ram pressure here, and then I totally ignored the magnetic pressure. That basically shrunk the magnetosphere in. This balance shows you that that will happen. When this ram pressure goes up, the magnetosphere gets smaller, etc. How about the moon? Anyone remember this is an even harder number to raise to the 2/3 power. Remember the distance in Earth radii to the moon? How high the moon? What? I think it's close. That's astrophysically right, 40. Actually, if you take 28 days, 24 hours, you have to raise that ratio. I get about 58, 60, okay? But well outside of that magnetopause, okay? So the moon is outside our magnetosphere, at least on the side we've just been talking about. And then let's skip that. Here, I gave you a very quick and dirty calculation of that, of how big that was and how this worked. Here are some of the state-of-the-art codes. Yeah, it's different. You get different answers if you really do this honestly, but I'd say to 0th order, in terms of gaining a basic understanding, the arguments we just went through aren't so bad, okay? Now, let's just quickly visit the other planets like Jupiter. Jupiter, same calculation would be done. The magnetic field strength of Jupiter is 15 times greater than the Earth at its equator. Okay, it's about 5 Gauss instead of 1/3 of a Gauss, 15 times. The solar wind, however, has fallen in density by 1 over r squared, 5 AU, factor of 25. So the Jovian magnetopause should be at 50 Jupiter radii. This is actually even a little smaller than what's observed. That is this huge number. It is much bigger than the sun. Right? The solar radius is 5 times smaller than this. So the Jupiter's magnetosphere is truly huge, mostly because the ram pressure of the solar wind is way down, and the magnetic field of Jupiter, because we showed that dynamo, it really has such a good dynamo that it generates a very strong magnetic field. All right, but very important, that was basically assuming the magnetic field of the Earth was confined to a spherical shell. That is not the case. We have the solar wind coming in. Now I will not ignore the magnetic field. It brings in magnetic field lines. The Earth has its magnetic field lines. We have, and I think you're going to hear about extensively this afternoon, magnetic reconnection that breaks magnetic field lines from the sun and the Earth and forms these magnetic field lines that start at the Earth and go into the sun, or start at the solar wind, and start at the solar wind and go into the Earth. What we call, these are also called open magnetic field lines. Okay, so we generate these new magnetic field lines that are basically open to the solar wind. And then on the tail side, which we haven't talked about at all yet, we're getting to there, they have to reconnect back so that the Earth's whole magnetic field doesn't just open up. So I get reconnection on the day side and reconnection on the night side in what's known as the neutral sheet. Okay, I'm going to assume that this reconnection occurs at subrate phi dot. That is, a certain amount of flux in Maxwell's is converted from solar wind to open, or closed to open, at a rate phi dot, Maxwell's per second. And in equilibrium, the night side reconnects the flux at the same rate. So we preserve a certain amount of flux that's open. And that gets swept back into the tail. That gives us a certain amount, there we want to say it, a certain amount of flux in the tail that just is basically in the process. It's been reconnected once and it's waiting to be reconnected a second time. Does everyone see that? It's kind of a balance. It's like, again, I hate to keep using toilets as an analogy, but we're always familiar with them. We have the tank in the back. Water comes in and it goes back out. The tank holds a certain amount of water, and on average, it has that certain amount of water. And it's the amount of water it takes to balance the inflow and the outflow. The magnetotail is the toilet bowl tank of the magnetosphere. It is holding the magnetic flux that has been reconnected on the day side and is yet to be reconnected on the night side. And it's going to be reconnected in this long plasma sheet and then swept back into the Earth. The length of this is something we really can't work out with these simple calculations I've been doing. It is very, very long. The moon is at 60 Earth radii. It's out here. So well outside this magnetopause, but inside the magnetotail when it goes through, okay, in this kind of cartoon picture. So in this magnetotail, the magnetic field lines from the night side are coming in here, going into the North Pole, going out from the South Pole, and just going way back down. And we have this place where the magnetic field is switching from outward to inward. It's a current sheet, right? Use the right-hand rule. You have current coming straight out of the page all along this sheet. Okay. And we have the same story at all these other places. Neptune as well. The boundary between these open and closed field lines, basically it's all the field lines that have been reconnected to the solar wind and are open and are waiting to be closed back down. That's some angles worth of field lines. And the boundary between these, open and closed, is what forms the auroral oval. Beautiful picture here of the auroral oval. Here is North America. There's Alaska. You can see Russia from there. You've got, etc. There is the ring that defines all of the magnetic field. Here, all the magnetic field is open to the solar wind. You'll notice the aurora is not created by particles from the solar wind, right? There's no aurora there. If you went way up and you were on the Franklin expedition up there, you wouldn't have seen aurora overhead because you're just looking at field lines that are open. It's this interface that gives you the boundary. You can estimate how much this is if you assume that the amount of flux in the polar cap is the same as the amount of flux in the tail, okay? And you can work out what that is if you know the latitude of the polar cap. So say that that's 75 degrees latitude, so you have 15-degree angle there. Theta of polar cap is 15 degrees. Then you basically have 10 to the 17 Maxwells. Maxwell is a Gauss centimeter squared. That's the astronomer's unit of flux. If you assume that that magnetic flux is in some uniform pressure, uniform magnetic field B tail, and put it in pressure balance with the solar wind, you can work out that you have a radius of a tail of about 25 Earth radii. So although it's only 12 Earth radii from the Earth out to the magnetopause, and another 20%, 18% of that out to the bow shock, if you go up from here, you go about 25 solar radii, and we get about 10 to the minus 4 Gauss in the magnetotail. Okay? Some beautiful pictures of aurora on other planets. Same story. I'm going to leave it at that. Right? The reason we have the structure of the magnetosphere we do is because our planet has a dynamo. So does Jupiter. So does Saturn. The dynamo is encountered by the solar wind, just as it is in Jupiter and Saturn. So you have some nice auroral ovals. This one you can actually see a bit of the northern and southern caps. All right, the last subject. We have to talk about the interaction between the magnetosphere that's created by this whole process and the ionosphere. Okay? Now, we have the field lines here that are reconnected, and I'm going to assume that the magnetic field from the sun is going to the south. This is called the southward IMF. It reconnects at this rate we've talked about, phi dot, and then it's swept backwards. So the field lines are being moved by this conducting plasma. They're frozen to the plasma and they're moved to the tail, and this whole field line moves. But wait, the field lines are frozen into the solar wind, which is moving this way, but they're also frozen into the Earth's core. That was our lecture yesterday morning. And that is not moving. I mean, that is moving at, what did we say, 0.3 of a millimeter per second. This is moving at 400 kilometers per second. So I can't move the feet of these field lines because they're frozen into the core of the Earth. True? Is that a problem? It is true that they're frozen into the core of the Earth. It's true that they're frozen into the solar wind. So the two ends of the field line then have very different masters. One is stuck at the core and the other is moving with the solar wind. This is a bit of a appealing to those people who have looked a bit at frozen in fields in plasmas. Why is a field line real in a plasma? And it is real. It's made of stuff. All the stuff, which is plasma, is frozen to the field line. So the field line basically has all this stuff on it. It's made of stuff. That's what it means to be real. Ghosts are not real. They're not made of stuff. It also means things like honesty is not real because it's not made of stuff. Okay, I have a very physics view of reality. But a field line is a real thing because it's made of stuff. And if it's got two ends and and one of them's moving and the other isn't, I mean, it's going to get really yanked around. Does this bother anyone? Does anyone see a way out of this conundrum? So the field lines are real when you have a plasma or any sort of good conductor where stuff is frozen to them. And the stuff, the solar wind, is moving at 400 kilometers per second over here, and it's going to try to move all the field lines back towards the tail. At the core of the Earth, they're frozen to this iron molten goop that is also an extremely good conductor. Magnetic Reynolds number, if you remember, was, I think it was 100 or something. Good conductor. So they're frozen going 0.3 millimeters per second, not 400 kilometers per second. So what gives? The answer is there's a gap between the solar wind and the core, known as the Earth's atmosphere and the Earth's crust, where the conductivity is not high. The field lines are not frozen. In fact, at that point, field lines could be considered imaginary. And in some of your classes, your teachers may have told you that field lines are just imaginary and they're not real things. And you have to forgive these misguided souls who told you that, because they probably lived in this gap where the conductivity of the stuff around them was not so high. Right? They lived in the Earth's atmosphere, stood on the Earth's crust. Field lines there are imaginary, so we don't even have to think about field lines there. In the core of the Earth, we think about field lines. They get all wrapped up. That's what created our dynamo. In the solar wind, okay. So we really want to think of the Earth's atmosphere as this insulator, and all the field lines essentially end right there, or at the ionosphere. This is what happens when you have a layer with some resistivity here, the ionosphere, an atmosphere that's a perfect conductor, and a solar wind, sorry, that's a perfect insulator, and a solar wind that's a perfect conductor. I'm going to move the material in the solar wind to the right as sort of an upper boundary, and watch these frozen-in field lines move with it. And I'm going to do this actually very sort of impulsively. I'm going to start with straight magnetic field lines. You see, I haven't drawn the field lines below here because they're imaginary below there. So I don't even really think about field lines. They essentially end. Now, I could trace field lines below this, and people will tell you field lines don't end. But I'd be tracing something that's imaginary, and that just, I don't like doing that. So I'm going to trace them where they're real, and they just basically end at the ionosphere. But the plasma moves to the right. The field lines get swept back. There's a layer of current that is just here where the field lines bend. You can use the right-hand rule. Field lines are bending. That creates current coming out of the page here. I've turned everything on its on the side. Field lines are coming out here. The current, right-hand rule, is going to the right. Now, I am not moving all, if you turn it on its side, I'm only moving a slab of plasma. So the field lines are only coming out within this region here. And so there's also current that has to come and basically enclose all of this. This is a thought experiment. It's not a simple thought experiment, but it doesn't have all that many pieces to it. Does everyone see what's going on here? I have flow to the right in the red arrows. It's sweeping the field lines back because this is the MHD magnetosphere, therefore creating a magnetic field that goes to the left, a current that comes out of the page, and minus V cross B, that is the electric field I see in the lab frame, is actually also out of the page here. But the electric field is everywhere above this current layer. The electric field and the current are not really related. Okay? The electric field comes from V cross B. The current comes from curl of B. Those two things have nothing to do with each other. Well, they have B in them. Okay. But, right? Does everyone see? This is where things get very, very confused among our two communities. Confused is a polite word for it. Okay? Tim can probably back me up, or Amitava, that the two communities have great, the people who study the ionosphere and the magnetosphere have difficulties right here. But I'm going to talk us through this. And the velocity does this. Okay. A little while later, that current layer has moved down. Basically, this layer of bending has moved down because the solar wind is acting. Now, finally, we get to this point here. The current layer, where the fields are bent, have moved all the way to the base. And it can't move any further because I no longer have an MHD plasma here. The current is now inside the ionosphere. Okay? At least this portion of the current is inside the ionosphere. The ionosphere is a resistor. Okay? So in the ionosphere, the electric field and the current are related. And it's basically E is J over sigma. So the electric field that here was created by V cross B, in the ionosphere, I can think of it as just being created by the current itself. And the current, which was created by the curl of B here, is still created by the curl of B. Okay? So I have current through the ionosphere. I have I have current through the magnetosphere that all came about for the same reason, curl of B, because I only moved one slab of material forward. So I have currents going down, coming across, and going back up again. Everyone see this pattern? Very simple thought experiment. The electric field in the atmosphere is basically the same as it is everywhere else. Why? It's a perfect insulator. It doesn't care about an electric field. Who cares? It doesn't care about a magnetic field. Okay, so we have the electric field everywhere now. It's basically uniform. It has different characters. Here it is V cross B. I still have velocity moving to the right. I still have velocity going into the page here. That's creating the electric field up here. Okay, and then we see that what really appears to be happening, because I've refused to draw the field lines below the ionosphere where they're not real, is it looks like the ends of the field line are just moving across the ionosphere, being swept by the solar wind. And they stop there because below that, they're not real. Okay? So we get this field line motion, and it relates to an electric field, which I can think of as creating the current in the ionosphere. Okay? Then I have these other currents that basically have to completely surround the slab of flux that I've moved. And this is what creates what's known as the polar cap potential. I have my field lines being swept back, going from position 1, 2, 3, 4, 5, 6, 7, 8, then all the way back around 9. Because after all, I have to get the field from the tail back out to the bow, to the day side, from the night side to the day side, so that it can be reconnected again. And if I watch those foot points move, and here we're looking at the north pole of the Earth, the polar cap, the foot points, which are being just moved along the ionosphere, where they stop being real, goes from point 1, 2, 3, 4, 5, 6, 7, 8, 9, forms this little swirly thing here, which through some great feat of imagination, someone referred to as convection. It has nothing to do with thermal convection. It is just a motion around in a circle. But this is called the convective flow. And I can take the electric field, which we argued is just coming from V cross B up here, but basically being put into the ionosphere as the same electric field, and I can integrate it from point A to point B. That gives me something known as the polar cap potential. That has to match, if you followed this whole argument, the rate of magnetic reconnection on the day side. The rate at which field lines are being supplied over here, basically they all have to pass through some line that connects A to B. So if I integrate that electric field, I get the polar cap potential. And so this is the version from the textbook. We have, this is a view. Here's the day side. There's the night side. Here is the convective flow. The foot points are moving from day side to night side, then sweeping back around. As you can tell, it's hand-drawn. This is A to B. I integrate the polar cap potential. There's also these currents here. These are the Birkeland currents. These are the parts that go along the magnetic field in the field aligned in the MHD region. So they come out of one side. What would this be? This would be the dawn side. They go into the dawn side and come out of the dusk side. Simple picture. And you can put in the numbers. Polar cap potentials are typically observed to be about 50 kilovolts. I think in your lab yesterday you saw some plots of polar cap potentials. They kind of looked like this in at least one hemisphere. So 50 kilovolts, if you turn this into Webers per second and then multiply by 10 to the 8, you get 10 to the 12 Maxwells per second. We argued based on the size of the auroral oval that we had 10 to the 17 Maxwells in the whole polar cap. So this basically means our toilet bowl tank is being replenished every 5 hours. I have flux going in at a rate of 10 to the 12 Maxwells per second, basically being stored in the magnetotail and then being flushed out through the night side at the same rate. So each one lasts about 5 hours. Again, that's an average. All right, that is it for the solar physicist's view of the ionosphere. Sorry, well, we're not really actually over time because we started so late. The whole ionosphere is created by EUV and X-ray photons. It's diminished during the nighttime, but doesn't go away because essentially you need to recombine it with ions, and then the sun rises the following day and replenishes it. The solar wind is deflected by the ionosphere, which is a conducting boundary, if there's no magnetic field, like on Venus and Mars. Otherwise, it's deflected by the magnetic field, the magnetosphere, and the magnetotail is created by this process of reconnection. Day side moved back to the night side and then swept back in. All right, that is the overview. Any questions on anything from the last 4.5 hours of lectures? Anything in our solar system that I discussed? Yeah. That's a good question. It puzzled me for a long time. In this simple model, what I've done is taken this. So here are a whole bunch of field lines. Do you see this? And they're all going straight down. And I am taking only a section of them, outlined here in orange, and moving them towards you. Sorry, moving them back, away. So I'm sweeping them back, but only those. So that creates a magnetic field out of the component out of the page here. That's why they're going to the left here, okay? But there's none here. Now apply the right-hand rule right here. I have magnetic field out here, no magnetic field there, and I get downward current. There's this layer of current that separates field that has been slanted from field that is just as it used to be, standing straight up. No component into the page or out of the page. Okay? That's the source of that. It's basically the boundary between field lines that's being moved and field lines that's standing straight up. Moved, standing straight up. I've got a discontinuity in the direction of the magnetic field. I have a curl, a magnetic field. Why are they field aligned? Well, what you have to do is picture that actually the field reverses across them. But if you pick an angle that's in the middle, the current is going in that direction. There's an average magnetic field that goes in that direction, and then a component that completely cancels. It's a very subtle trick of sums and differences. But it's created by the difference between field that's moved and field that isn't moved. Those are field-aligned currents. Yeah. Oh, yeah, sorry. I thought I mentioned that. This is the same thing as that, but viewed from over here. This is the view from over here. Okay, so if I look at these arrows here, they're going away from me. That's the little cross. If I look at these arrows here, they're going down and towards me, down and towards me. And here I can't see that there's some stuff in front of me that I'm not moving and stuff behind that I'm not moving. But in the slab view, you see that some is moving, some is staying straight up. Sorry, some of these diagrams take me like 2 days to produce, and then I throw them at you so quickly that you can't digest them. It takes me 2 days to make them. Any other questions on? Yeah. The polar cap potential? Yeah. So I would answer. I don't know. This is not something I know from an observational standpoint. But I would turn your question around and say, well, so point out that the rate at which it's reconnected here is roughly the same as the rate at which it's moved backwards. And that is so there's the rate of flux transfer. This is the polar cap potential, A to B. So my understanding is somehow, and I can't tell you how they do this, they can measure the potential in the ionosphere. I will also point out that that electric field that's in the ionosphere is also present below the ionosphere. So naively, one could say, I could just measure this from the ground. It's not that easy, but the electric field that's due to the reconnection is imprinted on the ionosphere and will be present below the ionosphere. So that's one way you would do it. Specific, I'm sorry. Tim, do you know how they measure polar cap potential? I see it come out of super darn. That doesn't mean anything to me. Yeah. What kind of instrument? Yeah, he's asking about which instruments do it. Okay, yeah. So, yeah. Yeah. I didn't, yeah. I did not go through all that details. But we could talk about that. I could talk about that for hours. The actual mechanisms from the solar corona where we get X-ray and EUV emission. We should, there's a huge amount of interest in that specific topic. I love it, but, or we could go upstairs and talk to Phil Judge, and he could talk to you for literally years about that. Anyone else? Questions that might be slightly easier to answer. Okay, let's take a break and we'll get back here. I'm afraid it's only 15 minutes, but. Yeah. I should never. Doesn't disappear, the ionosphere. That doesn't disappear, but its density goes down because the production stops. Right? Oh, sorry. Oh, yeah. It doesn't. They don't really disappear. They don't really disappear. Yeah. So what you could do, this is a philosophical issue. You can of course trace magnetic field lines wherever you have a magnetic field. So you can trace them through the earth, through the air. And people do that. And then you get div B equals 0. But there's a big difference between the magnetic field lines you trace in the air and the magnetic field lines you trace in the solar wind. The difference is in the solar wind, if the material moves, those field lines move with it. They're frozen. So they have some real tangible existence. They're real. In the air, they're not. I could draw a different field line over here. The air won't move with it. So essentially, they're kind of like this ghost. So I could trace the ghosts. Yeah. So I thought a simple picture to have for you was to say, stop tracing them. Just think of the ends of them. And they don't end because of what you just said. But the realness of the field line ends there. And it just gets dragged across the ionosphere. And what you observe as the polar cap potential is a result of that motion of that end. Maybe this is more confusing than the other view, but I've seen the other view lead to so much confusion.
Yeah. I'm never there.
Yeah.
I'm higher up, so I don't have to.
So
bother.
yeah, me too. I don't ever work in these things. So for me, field lines are always real. Everywhere I go, field lines are real. Yeah. So I never stop tracing them. They never end anywhere. Yeah.
But usually we think of the flux tubes instead of field lines because
Okay.
you start talking field lines.
Sure. Same thing with flux tubes, though. You could trace a flux tube through here. But if I were to move the air, does that flux tube move with the air? Not really. I know some other people would put out if you had like a little bar magnet, right? Let's make it a circular bar magnet, and I can trace field lines like this. And now I'm doing this this is in the air. Imagine this is a magnet. And then I spin the magnet. Do those field lines spin around with it? Well, what's moving in the air as a result of my turning this magnet? Nothing's moving. No. I would argue the answer is kind of, you know, it's like it's you know, there's no right answer to that because the magnetic field lines aren't real in the air. So, you know, now you're talking about like angels on heads of pins. It's like the answer could be anything you want because angels don't really exist. And so,
But I can understand why this.
yeah. I think that there shouldn't be.
We're treating different things, but
Yeah.
we kind of feel like it's
The-
the same.
And the physics has to, it's the same physical laws apply in both cases, but they're different parameter regimes. And in one parameter regime, the magnetosphere, the conductivity is so high that a really good conceptual tool is to picture these field lines as if they're real things. And so if I see the flow moving over the Earth, I know all the field lines are getting moved with it. Then you get down to the ionosphere, and that tool fails because of this idea of frozen or flux tubes fail. I can trace flux tubes, but they don't give me any insight into what's happening. They're just an exercise in following field lines, which is fun, but doesn't give you any real insight. If you imagine, if you just say, well, if they're not giving me any help, I'll just stop tracing them there, and then say that the ends are just moving across the ionosphere. And the electric field in the ionosphere doesn't have anything to do with V cross B. Yeah. I admit it's a very, I was taking a stab at trying to avoid that problem, but I probably created 5 other problems. Yeah. Yes. Yeah. Okay. All right. Oof. I'm done. Oh, you like that? That was what I understood about. Oops. Oh, there it is over there. That was a lot. I agree. And you know what? I didn't even in charge. Who's supposed to talk? My understanding is the radiation belt physics is becoming very important.
morning. You've had 3 excellent lectures from Dana Longcope, overview of heliophysics. And as he ended by saying, he was giving a solar physicist's view of different aspects of heliophysics. What he didn't tell you is that he's also trained as a plasma physicist. That's when I knew Dana, when he was a young student getting out of Cornell. And so a lot of the material that he talked to you about was very well informed by ideas from plasma physics. Plasma physics is the underlying discipline for heliophysics, but heliophysics is not the only place where plasma physics was done. Historically, plasma physics came of age over the last 50 years or so with joint stimulus from fusion, space, and astrophysical plasma physics. And a lot of the foundational work was done by early pioneers who were beginning to think about plasma physics, names such as Chandrasekhar, Alfvén, Dungy, Marshall Rosenbluth, and so on and so forth. We were fortunate to have, I think, great masters who laid the foundation of the field in some very sound physical and mathematical terms. I myself am trained as a theoretical plasma physicist. That's where I first began, and I actually began in the fusion program where I was a graduate student at Princeton many years ago, and then I left only to return more recently, 30 years later, teaching in the same department that I graduated from. To me, my perspectives are really that of a plasma physicist applying some underlying common concepts to as many systems as I can. And this may sound a little scatterbrained, but it really isn't, because if you approach the subject from this perspective, you will find that some of the same ideas recur. And so if you are in command of the tools of the trade, so to speak, then you will be in a position to apply it to whatever problem comes. So without any apology to you, I will mix up a fair amount of theory with applications. But I promise you it would not be to inflict one equation on you after another. I just want to guide you through some of the basic steps that you need to know in order to deal with this problem of large-scale instabilities. Clearly, by large-scale instabilities, I mean instabilities that can be discussed in the context of a particular model, and it will turn out that the model that I'll focus on is magnetohydrodynamics, in particular even ideal magnetohydrodynamics, for reasons that I'll go into in just a moment. But then I'll apply it to various contexts in heliophysics. Feel free to stop me any time during this lecture. I do not have so much material that I cannot afford to take your questions and answer them, so we'll just proceed slowly. Before I move forward, I should tell you that the material that I'm talking about can be attributed to a number of classic papers. I do not have the time to give you the citations for all of those papers, but the material that I'm talking about is largely to be found in textbooks. Many of those textbooks are on the table near the door, including one that I co-authored with Don Gurnett. I'm not shameless enough to advertise my own textbook because I consider it as one among several books that you have available to you. Any of those books will do in terms of your following up. Unfortunately, this particular topic by itself is not one of the chapters in heliophysics textbooks, volume 1, where it would have belonged. So I've borrowed material from other sources in order to make this up, and I've had very good help from Nick Murphy, who is a solar physicist at the Harvard Center for Astrophysics, and Ping Zhu, one of my own postdoctoral fellow colleagues, who is now a professor at USTC, China. So let me begin at the beginning with a mechanical analogy. What is it that we study when we study instabilities in systems? And this mechanical analogy is helpful because it first clarifies that there are systems which first we have to think about as being in equilibrium before we start discussing whether they are stable or not. So an assumption underlying all this work is that a system left to itself or set up in a particular way can be in an equilibrium state. Simple example, a marble in a cup or a bowl, you put it on a table and let the ball come to rest. It will come to rest at the bottom of the bowl, and that's an idea of a stable equilibrium. Why is it a stable equilibrium? Because if you perturb that ball slightly, it will return to its original position, and in fact, if there were no friction in the bowl, it will continue to oscillate about that position forever. But what really happens is between the marble and the bowl, there is friction, so the initial kinetic energy that you gave to perturb it goes to zero, and the ball comes to rest. You therefore return to the same place where you began. The ball shows its great reluctance in moving away from where it was and returns to it. That ball is in a stable equilibrium. On the other hand, if you turn the bowl upside down, it will take some dexterity on your part to put the ball on top of the bowl and let it be there. You have to work on it. Hopefully nothing perturbs you too much and the table doesn't shake. The ball sits. But if you perturb it a little, it will slide off. That ball will not return unless you choose to put it back again where it started out from. This then is clearly an unstable equilibrium because by perturbing the ball slightly, you moved it very far from its equilibrium place. Now, I said there were small perturbations that would do the motions that I just described to you. But suppose if you take this ball and gave it a very big kick so that it went over the boundary and came here. Well, that ball you have managed to replace, to displace significantly from where it was. What was the key? The key was that you gave it a very, very large perturbation that it actually went away from where it was. So something that is linearly stable may be nonlinearly unstable in that it moves away from its equilibrium place because the perturbation you gave it was so large that you got the whole ball into another place in the mechanical system. We will now look for where it can be, and it turns out in this particular case, this is like neutrally stable. It will continue moving around in this part of the table without sliding back. We will not deal here with the subject of nonlinear stability. That is a whole separate object in itself. I will make a few remarks on it, and in fact, by the end of the lecture, I will make an application to magnetospheric physics where the idea of nonlinear behavior of a linear instability will be dealt with. But this will be done mostly by the use of computer simulations. The study of linear stability, though, can be done by using pen and paper, using methodologies that are quite well established and so much part of our toolbox that they can be found in standard textbooks. Okay? So let me make that a little bit more precise. Mechanical analogy. how would you formulate this problem mathematically? This is freshman physics that you know about, which is that if you have a system in a conservative potential, let's say one-dimensional potential, which is described by this function W of x, then the force is typically the first derivative of that force function. Example, you have a spring mass system, half kx squared is the potential energy. If you use this formula, you get minus kx, where k is the spring constant. That gives you the force, restoring force on a point mass if a spring is displaced from its equilibrium position. Example of that. When does the equilibrium occur? When the first derivative vanishes. That then corresponded in the mechanical analogy to us picking the point in x where the ball had come to rest. Right? Easy enough? Well, how do we deal with the issue of stability? Well, now that the ball is at rest at the bottom of the bowl, we expand the function w of x in a Taylor series. First term is w of 0, say, if the ball is initially at x equals 0. The second term is plus w del x multiplied by delta x, but delta w del x is 0, right? The constant doesn't matter. In potential energy, you can always subtract that off. Potential energy is always undefined to the extent of a constant. So then after you go beyond the equilibrium position, the change in w due to a small change delta x is given by this function. Now, when is the system stable? The system is stable when physically you give it a perturbation and its potential energy actually increases due to the perturbation. The system will tend to resist that. Hence, the condition for stability becomes when the second derivative is actually positive, that is delta w greater than 0. Are you with me? The ball, on the other hand, on top of the sphere, when it is sliding off, it actually has delta w, second derivative of w with respect to x less than 0. So this then distinguishes stability from instability. If I have a potential energy functional, to summarize, you set its first derivative equal to 0, you find its equilibrium. You set the second derivative, then you calculate the second derivative, and the sign of that determines whether the system is stable or unstable. Are you all with me? Okay. I know this is very elementary, but it will get hard quite quickly. Believe it or not, a lot of what I am about to do today is this basic idea. It just is that our systems are complex, so we need to figure out what is the right potential energy functional is for these sorts of systems. And most of plasma instability study, in some form or the other, is related to this very simple idea. Well, I just looked up plasma instabilities on Wiki in preparing for this lecture. And it's a very discouraging list. It's a very, very long list. The plasma finds insidious ways in which it can go unstable and torments you. This has been the bane of the fusion program, that we seem to know how to get plasma in equilibrium in order to put the ball in the cup. But to find the ball in a minimum part of that cup is what has been the challenge, because the plasma is insidiously clever, more clever than any of us are in becoming unstable. So you have this rich literature on instabilities of various sorts. Needless to say, we'll not cover all of this in this hour and a half. In fact, only a very small but important subset of these instabilities. This is just to give you a sense that this is what this is about, and it probably takes more than one course to do justice. And there are very different kinds of instabilities that a plasma is capable of. What we are going to focus on is large-scale instabilities, and in particular, those that can be described by the MHT model. Now, there are two lectures today. This, the first lecture, will focus on what I call ideal MHD instabilities. And the second lecture is on magnetic reconnection, which deals with non-ideal forms of instabilities and their nonlinear behavior. So I'm going to start out with ideal MHD, but before I head deep into the subject, I'd like to lay out what it can and cannot do. Now, first of all, ideal MHD the word ideal means that you have magnetohydrodynamic equations in which there is no dissipation. How many of you are already familiar with the MHD equations? Aha, some hesitant hands. You don't have to worry about not knowing, because I'll start from scratch anyway, but that just tells me that I should spend more time discussing the equations as they come about. So, then a few words about magnetohydrodynamics. Dana Longhope already made quite a bit of use of MHD equations, certainly the induction equations in his dynamo lecture, but he also did more when he talked about shocks. He used Bernoulli equations. All of those things that he used are derivable, mostly from MHD equations. And this is roughly the analog of Navier-Stokes equation for ordinary fluids, with the viscosity set equal to 0. As you know, fluid dynamics is a study of essentially one equation, very elegant and a very difficult equation called Navier-Stokes. If you put the viscosity equal to 0 and deal with incompressible fluids, you get an equation which is called the Euler equation, in which you have forces that could be due to the pressure forces of a fluid, gravitational forces, and so on and so forth. MHD is nothing but hydrodynamics of a magnetized fluid. So you will have electromagnetic forces playing an important role in describing the dynamics. Now, ideal MHD, which is what I said I was going to focus on, is frequently used to describe large-scale instabilities characterized by low frequencies and long wavelengths. And let me make that more precise. What do I mean by low frequencies? By low frequencies, I mean frequencies that are much smaller than the cyclotron frequencies of electrons and ions. By long wavelengths, I mean wavelengths that are much larger than the Debye length. So issues to do with charge separation or plasma oscillations, otherwise known as Langmuir oscillations, are outside of the scope of the MHD model. To treat them well, you will have to deal with different systems of equations, and they can be done with either fluid or kinetic equations. I won't talk about them today, for the simple reason that plasma oscillations typically correspond to small wavelengths and large frequencies. To give you an example, the opposite of where our range is. Why are these? Because often these instabilities are the ones that have the potential to completely destroy, when they are really violently unstable, a particular plasma equilibrium configuration. Whereas the more small-scale instabilities, though they're very important, often preserve the overall integrity of the plasma configuration, but can cause turbulence, transport, and so on and so forth. All of those are extremely important subjects, but things that we are focusing on today have more to do with the large-scale stability of systems. Example, in heliophysics, substorms in the Earth's magnetosphere can completely destroy the magnetotail and can rebuild, which can be rebuilt again by the intervention of the solar wind. I'll discuss magnetotail stability a little later in the lecture. Or take, for example, an eruptive flare. You see these beautiful images of the sun, and then a flare occurs. And you lose large-scale stability of magnetic loops or arcades. And this will be the subject of Professor Longhope's lecture a little later today. Now, I should point out the limitations of ideal MHD. It's often a questionable model in weakly collisional plasmas, but describes well instabilities that grow rapidly. In other words, I'm saying that a plasma is never really ideal. There's always dissipation. Why is it then it's okay to use ideal MHD? It's okay to use ideal MHD despite the presence of dissipative terms if the instability growth rate is so rapid that the effect of dissipation is not felt much. So even though the system looks ideal, it can have a domain of validity. And when I'm talking about things that grow rapidly, I'm really talking about things that grow rapidly on an alphane time scale. You can get alphane wave dispersion relation very simply from the equations of MHD as alphane did, both linearly and nonlinearly, without invoking any dissipation. If you include dissipation in the problem, you can modify the alphane speed somewhat, but really for all practical purposes, if you're dealing with very weakly collisional plasmas, those collision frequencies, weak that they are or almost non-existent in the magnetosphere, do very little to stop the progress of an alphanic instability. Therefore, for the treatment of those instabilities, it's all right to use the equations of ideal MHD, though really the plasma by itself cannot be said to be ideal. You understand me? Say yes, just so that I know that you're not falling asleep. Now, the kind of instabilities that I'm going to be talking about, instabilities grow in systems because they have free energy, right? A vacuum field doesn't have instabilities in it. Why? Because it's so low energy in the first place that there's nothing that grows in it. So you need to put in some sources of free energy in order for the instability to grow. For systems that obey the MHD equations, and I'll demonstrate that in a very clear way, is that there are two primary sources of instabilities. Do you want to take a guess on what these sources of instabilities are in plasmas? Can you hold a lot of plasma pressure without having some catastrophic consequences? Imagine you have a little plasma and you have a magnetic field and you keep building more and more, add more and more plasma to it. Pressure builds up, right? So gradients of pressure could actually potentially drive instabilities. Sort of an intuitive feeling. Current densities, if they become very intense, are another important source of instability. In fact, for the linear stability problem, these are it. You need to worry about only two sources of free energy primarily. In a static plasma, if the plasma is rotating, then you can have velocity. Velocity shear can be a source of a lot of this instability. The problem of having velocity shear in a stability problem makes the problem mathematically quite complicated. I'll come to that near the end of the lecture when I'll give you examples of where velocity shear plays a role. But in the very beginning, I'm going to focus on two sources of free energy: gradient pressure and current density, and show how they can drive instabilities. Why these instabilities are very important is because, as I said, they can grow nonlinearly and destroy a plasma if they're sufficiently virulent. I give you examples: substorms in the magnetosphere, flares, or coronal mass ejections in the solar environment. And at the present level of our understanding, we believe that these are due to some form of instability, but the word instability needs to be made more precise. When MHD instabilities do not lead to explosive behavior, they can produce turbulence. Okay? Example, solar wind turbulence. It has been understood for a long time that solar wind turbulence is produced due to the interaction of nonlinear alphane waves. at a very zeroth order level, though not completely, this can be understood from MHD theory. However, as it has turned out, observations have pointed out that MHD theory by itself is not enough to explain all aspects of turbulence. How does a solar wind heat itself? Kinetic processes therefore become tremendously important. But the point of departure in those studies is usually ideal MHD theory. And then you find that that's not quite enough. It explains a number of features and leaves unexplained important aspects of dissipation and heating. We need therefore to put in more physics in the model. So the point that I'm trying to make here is that MHD is a useful point of departure even when it needs to be improved by including kinetic or non-ideal effects. This is often somewhere where we begin. This is how the theory was built up. And the theory has gone much further than I would be able to go today's discussion. So in astrophysical objects, I should also point out that heat conduction and radiative cooling can be very important effects. This is not traditionally included in the textbook variety of MHD theory, though now more books and more specialized books and papers are being written to deal with these problems. I won't have the time to get into this except to mention that you should be alert on where what we are learning today will break down. And these effects, these are very important effects in the sun's environment, let alone other astrophysical objects, and we won't be able to talk about that. With me? Okay. So let's begin on how we go about studying plasma stability. Think of the mechanical analogy. What did I say? First, we have to start with an equilibrium, right? So what is a static MHD equilibrium, by which I mean I won't deal with the complexity of a plasma that is rotating. Imagine the plasma is stationary, well confined, time independent, and you look at the MHD equations and you balance the pressure forces with the Lorentz force term. So J cross B, the Lorentz force, is balanced by the pressure gradient. This is a classic equation that governs magnetostatic equilibrium. What is J? Is simply curl of B by Maxwell's equations or by Ampere's law. So really J, as far as MHD is concerned, is nothing but the curl of B. If you solve this equation, and it has an infinite number of possible solutions, you can get all the equilibrium solutions you want. In fact, the equilibrium problem, if we have an ignorable coordinate in the problem, is thoroughly understood in plasma physics. Fully three-dimensional equilibrium problems have still very interesting aspects that are unresolved. We won't have time to go into it here because we'll be dealing with some simple configurations and examining their stability. So our first attempt would be to actually define such an equilibrium. Then what we will do, just like in the ball cup analogy, we'll go and perturb the equilibrium a little. And we'll assume that the perturbation we are introducing are small amplitudes imposed on this equilibrium. So the equations of MHD, which are fully nonlinear equations, are much too complex for solutions. We will therefore linearize them. Linearizing essentially means that you will get rid of all the nonlinearities in the equation by assuming that the perturbation is a very small one. I'll demonstrate to you how we do that in just a minute in the next slide. Slightly perturb that equilibrium. Then consider how that perturbation evolves. If there exists a growing perturbation, the system is unstable. If no growing perturbation exists, the system is stable. And then to use a combination of numerical simulation experiments and observations to study nonlinear evolution of the instability. So this talk will have some aspects of analytical work, which is very solid, foundationally very good, and you have some really wonderful tools available to deal with the problem of linear stability. This is a great thing to know. It should be very empowering for you to know that you go into a study of heliophysics or a laboratory, and somebody asks you, can you tell me how you can study the linear stability of a system? You can begin in one place with one formulation of the problem, and you can always get it to work out. I find that immensely empowering. And this could not have been done only by computer codes. This had to be done at a certain level by doing a lot of analytical work. These days, one of the things that you should watch out for is that doing good theory doesn't mean running computer codes only. Plasma physics has, and heliophysics has evolved to the point where it might appear that most of the interesting problems that remain to be solved are nonlinear problems outside of the realm of linear stability theory. You saw that long wiki list. And there are lots of papers associated with the linear stability of each one of those items. But we can't rely only on computers to tell us what are the right answers, because computers are basically dumb devices which pretty much do for us what we tell them to do. And they can calculate much better than us, but they don't understand things better than us. Now, it's not clear to me that we are getting a lot smarter while computers are getting smarter much more rapidly. But nonetheless, you have to basically go back to a point where you can analyze things, come up with an analytical model to try to understand what is going on in your computer codes. So even for nonlinear stability, we'll have to use a lot of physical intuition to try to understand what is going on from codes or from experiments. And I think that this is where building up your foundation really helps. Step by step, learn all the tools of the trade. So let's do this now step by step. Are you all with me so far? So MHD equations essentially deal with the 4 variables, 3, 4, 5, and 6. Density, velocity, pressure, and magnetic field, both of which are functions of position and time. Write them as a combination of equilibrium density plus a perturbation. The equilibrium part does not depend on time. Velocity, there was no 0th order velocity, okay? Because we assume that there's no velocity shear. If we had constant velocity in the system, you can transform it away by Galilean transformation. Therefore, you can move to the frame of that constant velocity, and you're back to a static problem. That is not what the problem lies. The problem lies when the velocity has a spatial dependence. You need to really deal with it. But here, we're going to deal with things which don't have that. The pressure has a 0th order pressure. Magnetic field has a 0th order magnetic field. The 0th order quantities obey the equilibrium equation that I wrote. J cross V by C equals grad P. And V0 is 0 for static equilibrium. We assume that the perturbed fields are much weaker than the equilibrium fields, and use the convention that the perturbed fields vanish at t equals 0, and then you build it up from noise. To 0th order, that's your equation. J cross B equals grad P. Now comes to the time-dependent equations in linearized form. Let's go step by step. How do we linearize equations? How many of you have done linear wave theory? Okay, well, then you know this. And I'm sorry if some of you know this material so well, it seems rather elementary. It'll quickly get harder, but I really have the desire to keep the class with me. And so the experts, please bear with me. Look at the first equation. The continuity equation is del rho del t plus del dot rho v equal to 0, right? So if rho is rho 0 plus rho 1, rho 0 has no time derivative. This has del rho 1 del t, only remnant term. On the right-hand side, you have del dot rho v. Linearization means that if you have two perturbed quantities, rho 1 and v1, you will drop their product from the equation because it's a product of two small quantities. Your goal is to keep quantities only correct up to first order. Therefore, that term, del dot rho v, gives you v1 dot grad rho 0 plus rho 0 del dot v1. Are you with me? Okay. Follow with pen and paper, or you can do this later on. Let's take the momentum equation. The momentum equation has rho dv dt on the left-hand side, where d dt is del del t plus v dot grad. But v dot grad v, that term, is a product of two velocity quantities, right? Now, if v1 is small and v1 dot grad v1 is second order. So on the left-hand side, the only remnant is del t of v1. Now, if you had zeroth order velocity shear, what I just said is not true, because you'll have a term that goes like v0 dot grad v1. Not here, because v0 is 0. The right-hand side is simply the pressure term. P becomes replaced by P1. This is your J cross B term. J cross B can have J1 cross B0, J0 cross B1, J1 cross B1. But J1 cross B1 is second order, so you drop it. So on and so forth. This is the induction equation that Dana used to talk about the dynamo. Linearize it, you get this. It turns out that the induction equation actually is a very simple equation if you just think of it by itself. What is the induction equation that Dana used for dynamo theory? Del B del T minus del cross V cross B equal to 0. That's a very interesting equation because B is linear, right? In that equation, there are no B square terms. That's all I mean, right? So when you linearize it, you get this equation, and it looks almost like the ones that he dealt with. This is the pressure equation, the entropy equation, ddt of P over rho gamma. And I won't belabor this point further. Here too, we have kept quantities only up to first order in perturbed quantities. And note that V1 is the only time dependent variable on the right hand side of equations 8, 10, and 11. That's not true. B1 is also, but B1 is tied to V1. So what really meant by this comment is that implicitly after you're all done and you take into account all these dependencies, everything finally really relates to only one perturbed quantity called V1. Do you understand me? In other words, there is a B1 here, but the B1 is governed by an equation which relies on V1. So in the final analysis, when you look at the right-hand side of this equation, everything depends on only V1. So what do we do with this now? So what people do in stability analysis and ideal MHD theory is that they introduce a virtual displacement of the plasma represented by this Greek letter C, which is the integral from 0 to t of V1 dt. Okay, so if you differentiate this equation, del z del t becomes V1. The attempt here is to write everything on the right-hand side of the linearized equations in terms of this displacement variable zeta. You'll see that because of that, you get a Newton's law for zeta, which is immensely appealing once you've done the algebra. And the algebra does take a few steps. Are you guys with me so far? Any questions? Okay. Yes? Thank you for asking. It's the ratio of specific heats, Cp over Cv, which is 5/3 for three-dimensional systems, but can be 2 for two-dimensional systems. In statistical mechanics, if you study that, it's usually 2 plus f by f, where f is the degrees of freedom of the system. Okay? So now let's go back. You know what I'll do, not because I want to bore you to tears, I'll show how you can take this nice variable zeta and rewrite everything in terms of zeta and get a nice result getting rid of some of these del del t terms. So go back to the continuity equation. I promise you that I won't do this with every equation that you just saw. I'll just give you the result, but let's just go through the simplest one. Del rho 1 del t equals V1 dot grad rho 0. V1 is del zeta del t. And you have V1 here, del zeta del t. Great. Now you can integrate this, right, from 0 to t, and the right hand from 0 to t. What do you get? Well, this is a pure differential. You get rho 1 on the left-hand side. This one becomes, because rho 0 has no dependence on time, you can take this out of the integral. This becomes a c, grad rho 0 minus rho 0 del dot zeta. Okay, so this equation now gives you the perturbed density purely in terms of the virtual displacement and equilibrium quantities. Go through this exercise, and this is done in textbooks. And let me just give you the results. You can, just the very exercise we went through for rho 1, you can go through for B1 using the induction equation and P1 using the equation of state. And then you collect all these terms, and you will find that all those 4 equations can be combined algebraically into one equation. And this is the Newton's equation for the linear stability problem. Are you guys with me? Okay? Trust me that you can actually do this algebra exactly like the way we did the continuity thing. Simply go and plug in del zeta del t, integrate over time from 0 to t. Do that for B, do that for P. Plug those in, combine, you get this. But this F is this force operator, okay, which depends on this virtual displacement zeta. Notice that this force operator is a function of zeta and all the equilibrium quantities, the quantities that you and I identified as sources of free energy, are sitting here. Grad P0, aha, current. So what's happening? All the perturbed quantities are becoming functions of these sources of free energy and the displacement. Even though formally done, that looks like a tough set of equations for arbitrary B0 and P0. Not having this term is really valuable. I'll return at the end of the lecture. That's what velocity shear does. It introduces an extra term in that equation that kills some of its nice properties, which makes the velocity shear problem much harder to analyze. Okay? Let's try our old methods of solving these equations. Zeta depends on R and T. What do? Variables separable. Imagine that zeta can be written as a function of displacement and time, product of the two. You plug it in those equations, you get 2 ordinary differential equations, one for T and one for zeta. So that this T is really written as e to the power I omega t, and the solution is of the form this. Very much like a harmonic oscillator problem, just more complicated because you're dealing with a plasma system where things depend on R and T. This is an eigenvalue problem. Since f is linear, everything depends on zeta only linearly. Remember, we threw away all quadratic terms in V1. So if all quadratic terms in V1 are thrown out, only terms that are linear in zeta would remain. And now you can solve this problem if we give you boundary conditions, what's happening at r equals 0 and r equals, say, if you're solving the problem in a cylinder or whatever, like an infinite plasma, what's going on at minus infinity and plus infinity, specify boundary conditions, you can solve this problem. And you can calculate omega square. It's strikingly reminiscent, just a more complicated version of Schrodinger's equation, right? People, you've taken your elementary quantum mechanics course, where you're given a potential, and you're given Schrodinger's equation, which is a linear equation. You can solve for all the eigenvalues and the eigenfunctions, right? Most of you have done that in some form or the other? Okay. And omega square, the interesting thing about this omega square is that omega square can be a discrete set of numbers, or it could be a continuous set of frequencies. That depends very much on the profiles you use to solve this problem. This operator F has a very, very nice property that gives you immense power in the stability problem. And I'm leading up to that. That this operator is self-adjoint. You've heard this word before, I'm sure, in your preliminary encounters with quantum mechanics or some mathematical physics. If something is self-adjoint, and if you have 2 solutions of that equation, then you could flip the order of zeta and eta, and this equation holds. For a proof, you can look at Friedberg's text. It takes a bit of doing, quite a few pages of algebra. When I teach MHT to my graduate students, this one painful exercise I make them go through every time I teach. You need to do it only once, just to satisfy yourself that you can do it, and then you can forget about it and just use this equation. But it's very important to do this once. So, if there is dissipation, F will not be self-adjoint. This is where ideal MHD really, really helps. But with that property, you can do a lot, okay? And let me just make a couple of comments. First is that you realize that F is self-adjoint, and that's great. And so you can say, what is the strategy for finding the normal mode solutions? Remember, zeta was written as a product of a function of r and time. We found all these eigenvalues omega, and you sum over them, and you get this normal mode. Because F is self-adjoint, the omegas must be real. Omega square, pardon me, must be real. What does that mean? What does it say for omega? If omega square is real, what can you say about omega? The frequency. Is always positive? Okay, that's one answer. If omega square is real, this you have to answer. I'm not going to answer this for you. There's one answer that has been preferred. It's partially correct. Big one? Positive or negative? Is that the only possibility? It could be purely imaginary. So it's either purely, omega is either purely real or it is purely imaginary. And as he said, if it is real, it can be positive or negative. Well, if it is positive or negative and the equation goes like e to the power I omega t, what does it say? It's either purely oscillatory. But if it is purely imaginary, positive or negative, what does I omega t give you? Growth, purely growing, right? Because I, suppose it goes like plus or minus I gamma, there's one purely decaying root and one purely exploding. There's a particular thing that we have left out. We either said something was purely oscillatory in ideal MHD or purely growing and decaying. But there are solutions in nature which oscillate and grow at the same time. These are referred to sometimes as modes with complex frequency or overstable modes. The word overstability is sort of a misnomer. It's actually a form of instability, because if the amplitude grows and overshoots, you really have something that is exploding as time is going forward. That sort of behavior is not allowed in ideal MHD without flow. You get it? If you're doing ideal MHD equations and you calculate and calculate and calculate and you have a bug in your computer code, and the code is spitting out frequencies that are complex, you know the code must be wrong. Because omega can either be completely real or completely imaginary and never complex. Because if it is complex, then it will have both an oscillatory and a growing component. Are you guys with me? Right? So ideal MHD does not allow you that, and I'll tell you when that breaks down a little later. So if omega squared is greater than 0, then things go, then omega can be positive or negative. Then the equilibrium is stable. It is purely oscillatory. If omega squared is less than 0, for any n, then the equilibrium is unstable. What does this tell you? That means omega squared positive and omega squared negative, which are separated by omega squared equal to 0, is a strict boundary between stability and instability. Right? Are you with me? Right? The marginally stable point, which is omega squared equals 0, is a very nice point to focus on. On one side of it you have stability, on the other side of it you have instability. So a lot of these calculations of ideal stability you will find are preoccupied with finding the marginal stability point, because they want to decide whether they're stable or unstable. They know that if they know exactly which profiles for which they are marginally stable, they know how to move on both sides of it easily to make it unstable. Now all we have to do is to solve for this. Now that's a hefty task, and it sounds straightforward, but I think that the problem of static equilibrium stability would be a lot harder if it were not for the fact that we have a really strong variational principle which is called either Hamilton's principle or the energy principle, which is in textbooks, that was first thought of by Subramaniam Chandrasekhar. It's there in his hydrodynamics and hydromagnetic stability. I don't know how many of you know about Chandrasekhar. He's no longer there, but he had an incredible ability to go into fields, work on it for a few years, discover theorems, tons of papers, write a textbook, and move on to another field, and never to look back what he left behind. MHD and hydrodynamic stability was one of those subjects, and he wrote a classic, and if you go through that, you'll find it. But the people who really developed that in their full glory are Bernstein, Freeman, Kruskal, and Culstrad, people who were involved in the fusion program, who developed this powerful tool called the energy principle to investigate the stability of all static equilibrium systems. And what was really powerful about the energy principle is that I wonder whether I'm actually missing a, am I missing a, I thought I had a slide here. I apologize. Do you have a slide giving you K, delta K and delta W in your presentation? For some reason, this is one. So let me explain. Do you have a blackboard? Let me write this down. Delta K, yeah. Actually a very simple idea. Is it okay, Nick, if I raise this? I have to define what that is. A darker one than red. That's the perturbed kinetic energy of the system. Half rho V1 square essentially integrated. Okay? And delta W is simply minus a half That's the potential energy of the system. You can show from the linearized equations that the perturbed kinetic plus the perturbed potential add up to give you a constant. That's no surprise to you, it's energy conservation. And if you take these two quantities, I had a slide where I had simply defined them in the manner in which I wrote, and take this ratio, omega square is given as a ratio. Now this you can see very easily. If you go back to this equation and you multiply it by C star on both sides and you integrate, you will actually get delta K on the left-hand side and delta W on the right-hand side, which the ratio of gives you this. Are you with me? Okay? Now what is really remarkable about this equation is that I don't know whether you know what variational principles are, but variational principles in quantum mechanics too, they're very, very useful. It is basically that it tells you, what variational principles tell you is that suppose you computed this quantity, C, delta W and delta K, okay? And imagine you don't know the actual solution to the problem. You chose what you call a trial function. some function that obeys the boundary conditions of the system. You don't know the real solution, so you make up one. Choose a function z, which actually obeys the right boundary conditions. You can then go ahead, choose a simple one, because hopefully you can do those integrals. You can calculate the omega square. What the variational principle tells you is that the omega square that you get by that will always be larger than the actual eigenvalue of the system. Okay? Are you with me? It will be larger. It's not the true solution. If it's the true solution, it will be truly the minimum. In other words, keep refining your trial function. If you refine it more and more and more and more, you will gradually converge to the true solution. But any trial function that you take, okay, is going to give you something that is higher than the actual eigenvalue. Now, this is not a property given to every operator f. Schrodinger's equation has this nice property, and why the quantum mechanicists like this variational principle very much is because when they have complicated interatomic or molecular potentials, they can solve Schrodinger's equation analytically or even by computer code very easily. So they like to make guesses on what the wave function looks like. They plug it into the variational principle. They get an eigenvalue, but the eigenvalue is sort of an upper bound for the true eigenvalue of the system. But then if they keep refining their trial function, they can converge on the true value. This sets up a nice method to actually calculate it. MHD is very similar. Ideal MHD is very similar without flow. Now, why is this so useful? I said that if omega square is negative, right, you have an instability in the system. Now, the trouble is that you don't want to solve the whole complicated problem. It's too hard sometimes. So you say, let me make a guess, a trial function. Suppose something goes to 0 at x equals 0 and something that goes at x equals 1. I don't know how to find the eigenfunction, but I'll take the function x multiplied by 1 minus x squared, just for the fun of it. Take, for example, a simple function c of x as x times 1 minus x squared. This vanishes at x equals 0 and vanishes at x equals 1. Suppose I'm solving a one-dimensional problem. I'm given these boundary conditions. I don't know what the true solution is, but I can make this choice. It at least obeys the two boundary conditions. It probably is wholly wrong compared with the true solution, but at least it obeys the boundary condition. So I plug it into this thing, and I calculate the omega square. What the variational principle tells you is that don't be despondent, because what you get is not so bad. Your omega square will be higher than the one you actually after, but you will be getting closer by improving on this function. Question?
How do you know what is the correct frequency?
I don't know. That's the beauty of the method. I will say I don't have the foggiest notion in hell what my real solution is. But what I can say is that I'll choose a trial function that at least obeys the right boundary condition. The mathematics tells me of a variational principle is that the omega square I'll get by that is not going to be the true omega square, but it's going to be higher than that. Now, imagine that the true omega square is actually negative, right? There's an instability in the system. So you go and choose a trial function, okay? And you find a negative value of omega squared. What does that tell you? The system must be unstable because it's not the true omega square, but I know that the true solution will give me an omega square even more negative. Therefore, all I need to do is, I don't care whether I can solve the whole problem or not. I can detect instability by choosing a trial function that simply is the simplest kind. That simply obeys the boundary condition. I plug it in, do these integrals. You can either do it by hand or do it on the computer, but you choose it's a simple integral that you need to do. If you get delta W negative, then there's going to be a true solution that makes delta W even more negative, as the system must be unstable. Without knowing what the true solution is, you already know something about its stability. Do you guys get this point? That is what makes the energy principle so powerful. That you wrote this complicated eigenvalue problem down, but if you want to decide whether the system is stable or unstable, all that you need to do is to choose a crude eigenfunction. And I won't even call it an eigenfunction because I don't know whether it is a true eigenfunction or not. I'll choose a function that just obeys the boundary condition, and if I can somehow find omega square is negative, then I can always assert that the true solution of the problem will make omega square even more negative, and therefore even that crude form gave me a negative omega square. It told me the system is unstable. In one paragraph, this is why the energy principle is such a powerful tool. Because you can determine instability or stability purely by choosing a crude trial function that obeys the boundary condition and calculating omega square. I know I repeated this many times to you, and to my graduate students I always do the same thing, because sometimes I write for general exams a little question, why is the energy principle such a valuable tool for stability? And this is the point. Everything else is just detail, okay? So people therefore have written big codes. And the whole, for complex systems, right? We can now write a computer code. And the whole point of these computer codes is choose a trial function, calculate this quantity, and decide whether you're stable or unstable. If you can get a negative omega square, who the hell cares whether you know the true solution or not? You already know the answer. Now, you may not get the true growth rate by that, because what you're getting for omega square is an upper bound, not the true minimum, right? So you have to keep refining things in order to get it or solve the normal mode problem, but you can certainly decide that something is stable or unstable. And this is what we are doing. Choose a trial function, a suitable choice, minimize delta W, a lower bound for the growth rate is given by this. Okay? Now, let's talk about physics. So what does this delta W really look like? It's a complicated looking object, and you can do the algebra given in books, and you come up with this form. This is a rather helpful form, and what I want to, just trust me with this, it's the delta W, the force operator and everything. I now want to talk about physics, because that quantity on top, the delta K below was always positive, so the positivity or negativity of this quantity is what is really needed. Now look at all the terms in delta W that are positive. This is the so-called field line bending term, positive definite, always stabilizing. This is the compressibility kind of a term. This one, sorry. This is another term which has to do with field line bending, just written in a more clever form. Here, kappa is the curvature of magnetic field lines. If you look at the terms in the equation, which are the two terms in this whole integral which do not have definite sign? Can you identify them? Look at them. Which terms do not have a definite sign? This and this, right? What do they depend on? Pressure multiplied by curvature, parallel current density. Remember my starting out this lecture saying what are the sources of instability? If these guys would be substantially negative, they can overcome the presence of these positive stabilizing terms. If you didn't have any current, and you didn't have any gradient pressure, the system is unconditionally stable. That's what I meant by saying if you have a vacuum field, and there's a deep reason for it. You know, if you have a little ball, and you have a vacuum magnetic field, right? Why is this always so stable? Because you can show that if you minimize the magnetic energy in that ball, subject to keeping the flux constant, then the state of minimum energy is called B equal to 0. In other words, that's a vacuum field. The vacuum field is the lowest energy state that you can actually have. It's got no current, no pressure. If we could do fusion with vacuum magnetic fields, we would have solved the problem even before we started. Unfortunately not. And these are also the sources of major instabilities. It doesn't matter whether you're in the magnetosphere or whatever, or the sun. This is in the sun, gradient pressure is often extremely small. Current density does everything for MHD stability. Not true in the Earth's magnetosphere, especially pressure, which can be quite large. The quantity beta, which is the ratio of pressure, plasma pressure to magnetic field, is a number that could be of the order much greater than 1 in the Earth's magnetotail. So it makes it very prone to pressure-driven instabilities that we will discuss. And so the first three terms are always stabilizing. The energy required to bend magnetic field lines, energy necessary to compress B, the energy required to compress the plasma. The remaining two terms can be stabilizing or destabilizing. And these are referred to as, so there's a nomenclature. If there are pressure-driven instabilities, they're referred to as interchange or ballooning instabilities. I'll get to the word ballooning in just a moment, and I'll explain to you what a ballooning instability is. It too is very much like an interchange mode, but a slight variant, and current-driven, which is associated with J parallel. Why is the pressure-driven thing associated with J perp? It's got to do with the equilibrium equation, and I just want to make that clear to you, is that if you have J cross B over C equals grad P, let me forget about C for the moment. Then that can also be written as a term that is parallel and a term that is perpendicular to the magnetic field. This equation has the same content as this. If you multiply this by B, this will drop out, sigma B cross B. And if you simplify this using vector identity, you'll be back for this one. This term is the parallel current term, right? It's in the direction of the magnetic field. This is the perpendicular current term. So when I write the associated with J perp, what I'm essentially saying is it's associated with grad P. So you can say it in one of two ways. Either it's parallel current density or proportional to gradient P. So what kind of instabilities do you get out of this? Say out of currents. You get a kink instability. The two types of instabilities we are talking about here. I'm sorry to have put you through this grind, but it's pleasing what you have. You have a very good place to start investigating stability. That's delta W. All that hard work you did came down to derivation of that one energy principle. And in that, you identified a very important piece of physics, that only two destabilizing terms are current terms and pressure terms. So therefore, in ideal MHD, there are only two types of instabilities. A kink type of instability is driven by current, or a pressure-driven type of instability, which is interchange and or ballooning. I want to first deal with the kink instability. What is a kink instability like? Takes a plasma column and kinks it. And we physically see why this is unstable, why this could be unstable. So suppose you started out with a straight plasma column and you kink it. Is it obvious why this will be unstable? Well, let's go back. The magnetic pressure is increased at point A because the field lines are more crowded, right below. The more closely crowded field lines are, the more the pressure below is. But on top, they're weakened. Now, will the column try to get back? Or will it continue to become more and more unstable? Imagine now the next step. You kink a little bit more. What is it doing? It's making the field stronger below and weakening. So what will happen is that the weaker spot is going to be pushed out more and more, and the plasma goes unstable. So what will resist this tendency? If you had an axial field that is extremely strong, then you have to bend it to do this. And because field line bending takes energy, as you saw in the energy principle, remember those big positive definite terms? If you can somehow make those terms really big, you can stop the kink instability. That's what a fusion machine like the tokamak tries to do. We won't talk about tokamaks here, but it actually runs with a very, very strong, what is called a toroidal field that sort of tries to stabilize it. Columns in the solar corona, where if the current density is strong, but there is a very strong guide field, it would be similarly stabilized with respect to kinks. So the kink, this is what I mean by saying, it could be along the axis of the rope, and usually what you find is this is actually distorting the whole column. So it's like a system size instability. You see a visual distortion of the column. I call that a long wavelength instability. If it were a short wavelength instability, it wouldn't change the configuration much. This instability is violent enough. It can completely break the column apart. And the ideal kink instability driven by current density is one of the most important instabilities in space plasma systems. I want to talk about pressure-driven instability. These are, you have to understand the idea of what is called good or bad curvature. And this is like a mirror machine. Do you know what a mirror is? The Van Allen radiation belts are formed. If you look at the Earth's magnetosphere, you get really strong magnetic fields near the ionosphere or polar caps, and weaker magnetic field as you go. That's really a mirror machine folded on like that, and it traps particles and things like that. Well, you saw this kappa.grad p term. That term you have to watch out for, and remember, we looked at this picture and we said, look at this term, kappa and grad p, and there's a negative term. If this becomes too negative, you can make this term overcome other things, right? So kappa.grad p is something that you need to look out for, and that's what I'm doing here. If it is greater than 0, then that can make that term very negative and potentially unstable. Okay, that means here is a plasma. What is the field line curvature here? It's pointing outward. Here, though, it's pointing down. Gradient pressure, it's always the plasma is here and is there, so the gradient of plasma is always pointing this way. So if you are in this part of it, kappa.grad p is actually less than 0. But here, it's bad curvature. You have kappa.grad p greater than 0. If the bad curvature guys overcome the good curvature guys, then potentially the whole system can be driven unstable. This is what is called an interchange instability. It has an analog with the Rayleigh-Taylor instability, which you may know about from hydrodynamics. A light fluid against a heavy fluid, you know this, right? So, I mean, this was a nice high school experiment that you like to do, is that suppose if you take a glass and you put in water, and then you took salty water and you very gently rolled the salty water down the walls of the glass, so it just came to rest on top of the lower water, which was less dense. And you could hold the tube upright, and soon enough you will find the slightest perturbation mixes the whole thing up. It's very hard to support a heavy fluid and a light fluid in the presence of gravity. These instabilities are totally analogous to these Rayleigh-Taylor instabilities, in which the light fluid's role is really taken up by field line curvature. You don't really have gravity, but curvature mocks the effect of gravity in these problems. So these are the interchange instabilities are a variant of the Rayleigh-Taylor instabilities that you know about. And so here I want to draw a little cartoon and show this to you. It's called Rayleigh-Taylor Parker because Parker took Rayleigh-Taylor instabilities and applied them to molecular clouds. And he talked about molecular clouds have strong gravitational pull. Gravity is a very important thing. And Rayleigh-Taylor Parker was essentially the stability of a system with gravity pointing downwards, gradient density pointing upwards, potentially an unstable system. And you can analyze that using the hydrodynamic equations. You don't need to do any plasma physics for that. It's also often worked out in plasma physics textbooks. I want to explain to you the role of G is being taken up by kappa, as I was telling you. Gradient pressure is still there, very much like gradient density. This is what the bad curvature region was, and you have interchange. Now, these interchange instabilities have the property that the wave number for the instability dotted with the B field is always 0. Okay? Now, what happens is that you know these plasmas, take the magnetospheric plasma or the solar plasmas, they are anchored, right? They don't, unlike toroidal plasmas, they actually begin on a surface and they come back and hit another part of the surface. So they have what is called line tying. What happens if you have line tied systems where the magnetic fields are frozen into certain boundaries, you can show that you actually stabilize the interchange mode if the surfaces on which the field lines are anchored are very close to perfectly conducting, which they never almost are, but it's a good approximation. So you say, does it mean therefore that if I have this sort of anchoring, I'll completely get rid of the interchange modes? Not so fast. The plasma is insidiously clever. It still wants to drive itself unstable. So what it does is to excite a different kind of instability where you don't have to perturb the end surfaces very much, but you actually perturb locally wherever the curvature is bad. Have you ever seen a hose pipe that sort of has had its lifetime slowly decaying? When you run water through a garden hose, if there are weak places where the curvature is not good, what happens? It forms blistering like structures and it puffs up locally. You must have seen this in hose pipes, right? Gardening at your home or whatever, or spraying the lawn. Eventually, those can grow larger and larger blisters and can burst out of the pipe. Ballooning modes are those blisters. They don't perturb everything in the pipe. They can leave K, they adjust the K in such a way that they exploit the curvature without experiencing any change at the boundary conditions. So ballooning modes, you'll hear this word, is a variant of the interchange instability. It just is one that knows how to survive. It's more general than the interchange instability in the presence of curvature and pressure. They are often used interchangeably in heliophysics literature. So I don't want you to be terribly confused by this, but just a very minor variation of the theme. Okay. How much time? We have about 20 more minutes. You want to take a break or should I continue? Want a break? Okay. A few minutes and then I'll wrap it up. Thank you. Want to do application to the magnetosphere next.
You know the solutions you were saying that you get from the wave equation, or
The ideal MHD force operator equations.
is that the same application?
The search for an energy principle for kinetic instabilities has been made for a while, but the problem with the kinetic instabilities is that the operator, you can follow that same process. You get an equation like that, but the F is not self-adjoint. Then you can't get an energy principle. In fact, it turns out that static MHD equilibrium problems are the only ones for which this result holds.
I don't work with this very soft.
It's always complex in general, right?
But that's a similar method of solving it.
Yes.
That's what they use.
That's right. And you can. What you're doing then is to solve the problem brute force, and that's all you have left, though. And there's not much you can do about that, you know, because the operator does not lend to a simple solution.
Trial and error. They can't find a solution.
Yeah. And typically when they find the solutions, what they find is that omega square or omega is really a complex thing. And even in these problems, if you put shear flow in them, they become complex.
About Rayleigh-Taylor instability, whatever is happening in this continent there,
Magnetic reconnection, so the magnetic reconnection was the subject of my later talks. In order to have magnetic reconnection happen, you need something on the right-hand side of your Ohm's law,
Yeah.
because the ideal MHD Ohm's law is E plus V cross V equal to 0, and that will never catch any reconnection.
Yeah.
Reconnection requires a certain dissipative term on the right-hand side. But you know, like for example, when these things kink up,
Yeah.
and they can sometimes go ideally unstable without necessarily requiring reconnection. Like the thing can erupt, like a kink. You think about this tube, right? Suppose you're twisting field lines, and the twist gets very, very high. What you're essentially doing is that you're building up the current density in the coronal tube. It can explode purely due to an ideal instability. It doesn't need reconnection. Now, whether that happens or not depends very much on what the drivers of the system are and on the current density.
Instability, yes, small movement will destabilize. Small movement
What I really mean is that, you know, the Rayleigh-Taylor-Parker dispersion relation, if you write it out, then you actually find that smaller wavelengths are actually more unstable.
Rayleigh-Taylor instability and for magnetic Rayleigh-Taylor instability. Also but because it's like water
Let
drop
me
on
see.
water drop on a surface. But if you put up more,
No, you're right. You're right. I mean it in a. I'm not being. Okay. You know what? There's a step here. The particular Rayleigh-Taylor that I had in mind here was one that was line tied. Do that, then the ballooning mode becomes more unstable. System, as I will show you. And those ballooning modes, the more the variation is direction perpendicular, those modes tend to be more unstable. No, fire hose is different. Fire hose is different. I gave the analogy of the fire hose because it's a purely mechanical analogy. The fire hose comes about due to a difference between P-perp and P-parallel. Here we have no anisotropy in temperature. Imagine that the fire hose is completely gone with T-perp being equal to T-parallel. Can you still be unstable if the pressure is high enough? It's okay, you guys following me? It's not too... No, that's okay.
King instability rely on parallel current, but I don't see at the equilibrium where is the parallel current.
Oh, the equilibrium is, so the equilibrium will be simply, you take a column, cylindrical column, and JB will have 0 radial component, B theta of R, BZ of R, and the J will have, in general, J theta of R and JZ of R. This is,
So just from this picture, it looks like both has.
oh, correct.
No. This and this.
That's right. That's
Right,
right.
and so there's no parallel current.
No. Well, but it's parallel to the magnetic field.
Well, it's perpendicular.
Okay, I see what you're saying. You're saying that J dot B, you know, this is very interesting, your point. In this case, it's really all J perp, but the J perp is not pressure.
Yeah.
You know what I'm saying? So,
Right, but
so this becomes like a curvature-like instability, it would seem like, but it's really driven by current density. And so it is kink-like. In other words, it's a particularly, thank you for mentioning this point, it's a particularly degenerate instability because you can write down, J cross P equals grad P, right? In this case. right? Now, this is a really good point you mentioned. J perp is B cross grad P by B squared. As you say, the B theta is there in this picture, and there is in fact a gradient pressure here, which is a function of R. So let me see. The J perp is 0. Bz is 0. Jz, J theta is 0. So there is in fact, why am I confused? I have a feeling that the form of delta W we are using you know what? Let me get back to this question. You raised a very good point. I'll come to this. Can I think about this? Let's talk about this. I'll figure it. Okay. So, what I want to do is to quickly go over a really important problem in magnetospheric physics, which is the so-called substorm onset problem. And you've seen in Dana's talk a cartoon such as this. What happens in substorms is that when the interplanetary magnetic field actually turns southward, you have what is called magnetic reconnection between field lines which are pointing southward from the IMF and the dipole fields. And I'll explain magnetic reconnection in my next lecture. You have flux transferred from the left side to the right side and a thinning of the magnetotail. That thinning goes on sufficiently that you actually get a point where field lines are pointing in opposite directions. This is the so-called neutral point. Reconnection begins, and reconnection in a way that we will discuss later in this course leads to the phenomenon of substorm onset. And let me show you how this actually occurs, and these are pretty spectacular pictures, auroral imaging that actually develops. And when a substorm occurs, as I said, the magnetotail thins, reconnection occurs. That's a very rapid process, can become very rapid, and you actually get energetic particles that are liberated due to the reconnection event following field lines and hitting the aurora. And you look at the picture of auroral brightening, you will begin to see a spot that then proceeds rapidly and envelopes a good part of the aurora, leads to spectacular brightening. If you monitor what is going on in the Earth's magnetotail, say at distances of about 10 Earth radii or so, and you monitor the cross-tail current density that is pointing out of the plane of the paper, the current density shows very interesting behavior. That it shows a slow growth phase that lasts about 30 to 45 minutes, an explosive phase of growth of the current density that eventually causes onset and leads to current disruption. This entire phenomenon was actually described by Otani using single satellite measurements. This is a cartoon of his measurements. But since that time, due to Themis and other ground-based observations, has been put on much sounder footing. So in other words, if you're looking at cross-tail current density at about 10 Earth radii or so, then what you find is in fact that the current density goes through this spectacular adjustment. Notice that in 2 minutes, the cross-tail current density has pretty much gone to very high values to rather low values, which are typical of what is true of the dipole magnetic field of the Earth. The dipole magnetic field is a vacuum field. It's as if the whole plasma has unloaded spectacularly over a period of 2 minutes or so to give you substorm brightening. And the picture of substorm evolution that people have cooked up is that you actually get this X-line formation, distances due to things pinning down, and you don't know what reconnection still is, so I have to simply tell you that means when two field lines are coming together and they're actually undergoing reconnection in a way that is outside of the realm of ideal MHD. Why am I discussing this then in this lecture? It's because people thought for the longest time, and many of them still do, that the substorm comes about due to two reconnection events. One that occurs at distance of 20 to 30 Earth radii that leads to strong flows that slow down as they approach the Earth's tail, where there is an enormous cross-tail intensification that leads to a major second reconnection event that causes dipolarization. Whether that is so or not has been an unresolved problem in substorm physics for a very long time and still continues to be. The so-called 2-minute problem that led to a good joke once on April Fool's Day, where people got together in Japan and Kamide-san, who signed the email Kid Me, wrote this email. This year's Substorm Conference, 1998, was one of the most successful yet, with 250 in attendance. All existing paradigms were discussed at length, and during the wrap-up session it was realized that only the time of the events within 2 minutes of onset were still seriously under debate. In other words, people didn't question what was happening at nearer distances. The growth phase, fine, people understand. The cross-tail current density builds up, yeah, we understand. But when does this onset occur? And what triggers it? Is it another reconnection event? Or is it something else? Well, it seems foolish, Kamide-san argued, for a couple of hundred scientists to travel halfway around the world to argue over 2 minutes of geomagnetic activity. The substorm problem was declared solved, and no more substorm conferences are being planned. This was, of course, an April Fool's joke. April 1st, 1998, Chris Russell sent this out to everybody, and for a split second we thought he was being serious. No, not really. So what's the deal? The deal is really that people cannot make up their minds on what is going on at nearer distances. Now, Themis, science papers, and others have more or less made the case that reconnection is happening. But if you talk to Eric Donovan and others who are looking at ground-based observations, they rightly point out that the beta in these cases is extremely high, and the tail is very stretched. And there are some observations which suggest that the beta is sufficiently high that the curvature dot grad p term that we were talking about could drive the system unstable. That's ballooning. And therefore, this is an interesting situation where even though you started out with reconnection, whether you end the system with reconnection and the substorm onset is truly associated with another reconnecting instability, or whether it is driven by ballooning, is a matter of some debate. And therefore, a question arises as to whether the substorm can actually be unstable. If you look at the curvature and gradient pressure of field lines, look at this system. The curvature and gradient pressure produces a local region of what we call bad curvature. So the geometry is about right for the triggering of ballooning. And one can well imagine a circumstance in which there is competition between reconnection and ballooning. It is plausible that both may be competing and that there is no unique mechanism for substorm onset. Just allow for that possibility. How would you check it out? You would do exactly the kind of analysis that I showed you so far. You would numerically compute what a stretched magnetotail looks like with its gradient pressure, hopefully benchmark it with observations and have reasonable numbers. Then you do a delta W analysis. And what do you find? That yes, it can be unstable when beta, field line length, gamma, the specific heat you're asking about, current sheet width, the unstable parameter ky, can actually drive the system ballooning unstable. The question is, and this is what was done in some careful work by Cheng and Zaharia, who built up very comprehensive models of the Earth's magnetotail and simply used the energy principle and something equivalent to figure out whether this thing can be unstable. And the conclusion was, yes, when beta is moderate, something between 10 and 50, they found rather interestingly that if beta becomes too high, then you get stability again. Because there is this term in energy principle that goes like gamma p del dot c squared. There's a p multiplying that gamma, that pressure, that absolute pressure. If the pressure becomes too high, then that compressibility term can overcome the destabilizing term. So you get typically instability in a range between 10 and 50, which is very much where the magnetotail is. Well, what does this mode do? Well, what it does do is that it actually, and I'm rushing through this a little bit, it actually can become unstable to this ballooning mode. And what does it look like? Well, if you follow nonlinear evolution of a system, this is what it will look like. It will become unstable. Initially, you have a pressure profile that is kind of unstable, and the finger-like structures form, and the instability is growing nonlinearly. This now is coming from a nonlinear MHD code, which first did a stability analysis to identify the linear instability, and then followed through nonlinearly to figure out what the ballooning mode can do. And this can drive strong shear flows in the system, even if the initial configuration didn't have any flows in the first place. In magnetophysics literature, these are referred to as busty bulk flows. That was first discovered by Shiokawa, Baumihan, and others. And what has been found is that you can actually, driving things ballooning unstable, drive shear flows in systems which have the characters of fingers and bursty bulk flows that are widely measured by in situ satellites. So here was an example of a mode that first went unstable linearly, and you can then ask, what does such a mode do nonlinearly? Well, it turns out that this mode actually continues to grow exponentially rapidly, even in the nonlinear regime. And if you wait very, very long, then this eventually will saturate. So the question that you can ask yourself is this instability enough then to disrupt the current and produce the current disruption phenomenon? It turns out that this is not a complete solution to the problem, because even though this is a fairly virulent instability, it is not by itself enough to disrupt the magnetotail. So our temporary conclusions are that we do not know unambiguously yet, even though there are some people who have made up their minds, whether it is reconnection or ballooning which can cause substorm onset, or maybe both coupled together. In these sorts of problems, I've been able to study one and not the other. But maybe in a circumstance where both of these processes are coupled together in a three-dimensional system, that you will be able to find a plausible explanation of substorm onset. I still consider this an unsolved problem theoretically, because I don't think any theorist has yet provided a conclusive picture of how an instability develops from linear instability that produces substorm onset, and most importantly produce the auroral brightenings that we discern substorm onset by. And therefore, we have a very well-developed set of observations that still challenges theory. And as you can see, the tools that you developed will set you on the path to analyzing what some of the relevant instabilities are, and then zeroing in on computationally to do nonlinear stability theory. Let me end with that. There are some further things in the lecture, but I don't want to keep you any longer because an hour and a half. What I wanted to tell you was to put you on guard about systems where the energy principle does not work. And I pointed out there are two classes of systems. When you have velocity shear in the system, you cannot use these tools. Things like the Kelvin-Helmholtz instability cannot be described. They're very important for the magnetopause, for example. You cannot also do the magnetorotational instability in accretion disks, which is an extremely interesting subject in its own right, outside of the realm of heliophysics, but very much the same type of machinery. I would have loved to have spent some time on that, but we have run out of time. Maybe I went too slow. And that's a subject for another day. Needless to say, once you've covered the issue of ideal instabilities, let me quickly go to the end of my talk. Last slide, I lay out things that we don't cover. Resistive instabilities. This takes me to the subject of magnetic reconnection, which is in the afternoon. And then kinetic instabilities, which can be very, very short wavelength, discussed in the context of the kinetic equations, which is a completely separate subject by itself. Would easily take a lecture, and you have two-stream Weibull, Bunnemann, and these are also extremely important instabilities. But the emphasis of this lecture was in large-scale instabilities, low frequency, long wavelength that can be driven unstable, and the ones that we dealt with were kink, interchange, ballooning. And I hope you have a sense of when these things can become important under various conditions. Thank you for your patience. Questions? There were some questions on the break. Yeah. Sure. So, interchange modes, let's talk what interchange modes were. If they have a wave number, then they are characterized by the feature that k dot b, which means the wave number parallel to the field line is strictly 0. So if you're having interchange modes in, say, in a mirror configuration like this, you can interchange flux tubes without causing any perturbation along the field line itself. It is proven in textbooks that if these field lines are anchored solidly in conducting walls, which are perfectly conducting, what drives the instability, if you look at the physical picture, is essentially an E cross B velocity of the plasma particles, which experience that drift if, due to the motion of interchange, causes charge separation in the system. So if you have conducting walls, what happens is that these electric fields tend to get shorted. And therefore, you can show, and this has been done in many textbooks, that if you take a magnetic mirror, like I was showing good curvature and bad curvature, if you just put conducting walls at the two ends of it, you'll completely stabilize the interchange modes. Okay, then you say, now that's not a terribly good thing, because the ionosphere is not a perfect conductor, as you know. Neither in the laboratory do you want to put perfectly conducting walls at the end of field lines, because they'll bring in impurities into the system and cause cooling. So even though theoretically a great idea, practically is infeasible. But nonetheless, the instability is stabilized. So if you have a very highly conducting ionosphere, then you could say interchange will be reduced to a very innocuous instability. Ballooning is not like that. What ballooning does is that it actually causes small k parallels in region. It's not a uniform constant k parallel throughout, but k is not uniform, k parallel is not uniform throughout the field line. It actually has a finite structure parallel to the field line. So what it tries to do is to locate the eigenfunction in regions where the curvature is bad without perturbing things near the surfaces, local blisters. K parallel, therefore, is small, but not 0. This is the only difference between an interchange mode and ballooning. So you could say, isn't the interchange a special case of ballooning? Because suppose you took k dot b small, and then you take the small quantity to go to 0, you'll recover interchange as a special case. You would be right. So balloonings are generalizations of interchange, will allow for local k parallels. So they can play games with local curvature, where the curvature is bad. They localize all their action around those. That's why I said the hosepipe analogy in the garden. I didn't mean the fire hose instability. Somebody was asking me. Not at all. I was talking about something with scalar pressure that forms blisters on tubes That's ballooning for you. It tolerates a finite K-parallel, and you can redo the whole theory with a finite K-parallel. Of course, that's the equilibrium, that you have curvature in the first place, but if you somehow had line tying at the end, that tends to stabilize interchange. Ballooning's special character is it allows for a small K-parallel and diminishes the stabilizing effect of line tying. And it came about because systems which had conducting walls were still seen to be unstable to pressure-driven instabilities, and people couldn't figure out why is that so? Because we know, we can show rigorously that interchange is stabilized. Aha, it can still balloon. I mean, it's called balloon because if you have a balloon which has a local weak spot and you're blowing air into it, that spot blows out more. The balloon doesn't expand uniformly. You develop local spots where you see blisters coming on. That's how a balloon that has been used many times explodes. You see it's developing blisters locally. That's ballooning for you. Any other questions, comments? Okay. If not, have a good lunch, and we'll talk about reconnection after lunch. Thank you.